A very good morning to you all. A very good morning to you all. Today, we have three lecture sessions based on theoretical tools to design nanomaterials presented by Dr. Pandey sir and a tutorial session based on supercapacitors and electrochemical batteries, electrochemical characterization by Professor Jaydev from IIT Guwahati. So I welcome Professor Pandey to deliver his talk. Thank you.
Namaskar. Let's start the day 4. And my plan is to give you a glimpse of the results mainly coming out of our group to show you the capabilities of simulation models and what can we do with them. So before I start, let me see if Dr. Hingez is there. Can you check? Hingez. He asked one question yesterday, so I want to address it before I start. He's there? Dr. Hingez, you're there? If not, then I can, when he comes. Good. So yesterday you asked the question about simulation and what can we do. So just as you know, I'm sure you're aware of this graph, but for the other participants, that the X-ray absorption is really a very powerful tool. Besides diffraction, you can get really information about the local structure of that particular atom and surroundings. So if you look at the energy versus intensity, what you have is that there's a very sharp peak coming out. And this is called a edge structure. So X-ray absorption near edge structure, but after a while, then sort of it becomes flat and then a very fine structure, and it's refers to as X-ray absorption fine structure. And this mainly comes from the scattering of the ejected electron by surrounding atoms. So, Dr. Hinge, the simulation model, what we have is we can definitely calculate the edge structure, which is basically excitation of the electron from the core level to the empty level. But still, we do not have a means to calculate the fine structure, because then we need to take care of the scattering of this electron with the atoms. So I'll just give you one sort of result. This came out last year. So this is slide sort of tells us about this Zanus or X-ray absorption near edge structure. And I said is really sharp resonance peak, and it does provide the local bonding of the analysis. So what happens is once you sort of excite, what you have is that these are so-called the 1s, 2s, 2p, and 3s levels. So depending on case is referred, let's say nomenclature, the always electron coming out of the 1s deep core level is referred to as called K edge. And we have so-called the virtual states up here, the unoccupied. And then the S and P, they refer to L1, L2, L3, and then so on, Mn and other stuff. So what we had done is we looked into lithium polysulfide. Yesterday we were talking about the structure. And on right, you have a sort of the in situ results coming the X-ray incident energy versus the absorption. And you can this kind of peaks, for different materials. And from here, you can say depending on the peak, if you can identify, you can see here is coming out of the S8. So your sharp peak around 24, 72, 73. But when you have another polysulfide, it peaks shift in the red. And once you have the ionic compound, of course, it has altogether a different shape. So the calculation, what we had done is the whole idea to calculate the ground state total energy of the system, and you take out a electron from 1s level, simply take to the vacuum. And up here you can see we have the bulk, because the bulk results are available. S8 you can see on blue here and then black here. And you bring in Li2S, here experiment you can see there's a totally different shape, which again is not exactly, but it mimics the shift in the peak. And you further go on from Li2S to a polysulfide, Li2S3, you can see this peak appears. So what the thing is what we can tell the guide, the experimentalist is, as you move from Li2S to polysulfide, Li2S3, definitely you are going to see a small peak. This is called a pre-H peak, about 2471 EV besides the main peak. And that sort of tells you that indeed at the cathode, there's a formation of Li2S3. So you can see is experimentalists can observe the peak, but simulation can provide exactly which material is causing that peak. So it helps to understand the stability of the system in the battery framework. So Dr. Hingez answers your question. Is okay? Good. So let's move to the next three lectures. First, I'll look into the bulk material and see what we can do. And then we switch to graphene and nanotubes. And these are coming definitely mostly from our group. So let me summarize what so far we have learned in last 3 days. Is the key thing is, as a materials person, before we apply to energy-related applications, we had to determine and establish the structure property relationship in a given material. Then only we can see how useful the material is. Then we move to some of the concepts, going from an atom to molecule to crystal. The difference is this presence of periodic potential. And then we use the mathematical convenience to describe the effect by Fourier transformation to K-space. And then as you move from bulk to nanomaterials, what we have is the quantum confinement effect or energy quantization. So whole idea is to how to exploit the effect because of the size. That's the key thing. Then we looked into a lot of characterization techniques, diffraction, Raman, which is the vibrational mode, and the imaging techniques involving STM and an AFM. Then I moved to a little more theory. We talked about the bonding or binding in a given crystal, ionic, covalent, or metallic. And then we have the secondary one is coming from the weaker one, van der Waals interaction, and so on. And we looked into the carbon-based structure and realized that it really is the beauty of carbon, that it can form a SP, SP2, SP3 kind of bonding to give us a really variety of materials. Then we looked into the block theorem, which again is a consequence of the periodic potential. And from there, we moved to some of the methods to describe this many-body system. First starting is so-called decoupling electron and nuclei by Born-Oppenheimer approximation. And then we looked into the exchange. is two electrons. As you know, Pauli's exclusion principle cannot have the same spin state. So we treat the exchange. But the drawback of Hartree-Fock is it does not include the correlation, because what it assumes in so-called the mean field approximation, that this electron basically is floating around in the average field, which is given by the other electrons. So correlation part misses. So then we move to called density function theory. So the change is here we talk about the wave function, and density function theory talks about the density. And what it says, the theorem, Kohn-Sham, that we can definitely determine the exact ground state density of a system. And then it writes down the Hamiltonian. And if you remember, what we have is a little drawback here. We do not know what the exchange correlation potential is. So we had to pick and choose, and I'll show you some of the results. It depends on this exchange correlation potential. And then we looked into yesterday what exactly the current requirements are from photovoltaics. Is the band gap, which can absorb visible radiation from solar light efficiently, and then the carrier transport, photocatalyst. Here we looked into the generation of this electron-hole pair and this exciton binding. It has to be weak. And then we looked into the hydrogen storage. In a sense, the hydrogen, if you want to store in a given material, then the binding has to be weak, about a tenth of an EV, or a tenth of EV. And then we looked at the battery system, especially the lithium ion, and the challenges we are facing to move forward. So let's look at the theory and simulation results today, and we'll see if I can convince you indeed this structural information, and then we have this simulation tools. We can really determine property very accurately and reliably. So this is the slide is because, as you know, being a scientist, we had to have some kind of a motivation. Why do we want to do it? So we start with the hypothesis is that we had to provide the quantitative results, not the qualitative. The quantitative, and the advantage what we have is we can tap into the computational power. That's why we can do it. We can both predict the physical and chemical properties of materials. So it's a prediction. But before we go on to prediction, we have to make sure that how good our model elements are, how good our approximations are. So we have to rely on our experimentalist colleagues to provide some data so that we can compare simulation and experiment to see, they look pretty good. And once you have the confidence in your model, then you can move on and then help the experimentalist to either understand what exactly the phenomena is, or you predict. So this again is possible. So just a slide to refresh you what exactly we are talking about we have the many body system, we have electrons and the nuclei. And simply what we say is we have the non-interacting system where electron nuclei are decoupled. And it makes sense also because nuclei are heavier, electrons are lighter, and they move very fast. So they're not sort of include the response of the nuclei motion. So we can decouple it. And then we have some of the equations. And then, like I said, the drawback here is although it includes the exchange and correlation part in the Hamiltonian, but is not known, is only known for the model system. So we had to play around and look for the appropriate functional form for given material. So there's a very, very good book. It's a PDF is available, and I'll ask Dr. Singh to forward to WhatsApp if you want to get into not the theory part, but how to use a DFT to simulate. So that's our connects, more of an application. So, like I said, there are a series of approximations for this exchange coefficient function. Well known is called LDA, which sort of assumes the electron density in a material is homogeneous. So it really works for the metals, where is the case, but for non-metal, it fails. So then you move to called GGA, where you have the gradient, because in non-metals, especially ionic or covalent, what we had density is not uniform. It's sort of localized on the nuclei as well as in the bond center. So you have this gradient in density. So this GGA takes care of that, the physical sort of picture very well. And then, as you know, is once we want to improve the accuracy and we have more computation power, then we have so-called the hybrid, where you take the exchange from Hartree-Fock and then include the correlation from the GGA approximations. So what you want to do in our goal is we use so-called the variational principle. So we pick up a educated guess for the density of the system. So if I pick up, say, MgO, magnesium oxide crystal, so my educated guess is going to be magnesium atom and oxygen atom. Then we calculate the total energy of the system. And then we have called self-consistent field loop. So you calculate N, you guess N, calculate E, then from E you calculate the new N. And then E, so sort of you try to zero down or bracket in where the energy is minimum. And once we achieve this state, we call this is our ground state of the system. And this density is going to be the ground state density. So once you know the ground state density and the energy, you can calculate any property you would like to calculate or find out. So this is called the flow chart. Is about in this is self-consistent cycle. So we start with the initial guess, and then we have the effective potential. We solve a Kohn-Sham equation, and then we again calculate the density and energy, and we have a certain called convergence parameters. Like for the given energy, we are looking at the difference between the energies of the order of 10 to the power minus 8 to minus 10 eV. So it's a very, very small sort of a difference between energies. And if we achieve it, we say calculation is converged, and then we have the output. So trick of the trade is to find what is the minimum total energy of the system. And as you know, it all depends on how well your guess is. If your guess is poor, it's going to take forever. If your guess is pretty good, it can do it quickly. So over the years, it comes from the experience, and I call the feeling the system, that what kind of guess you would like to have it to get it converged quickly. So I think the question from Dr. Naidu, day 1 and day 2, what can we do and what we cannot do, and what are the limitations of this model? So let's start what we can do. So again remember, knowing the ground state energy and density, we can move on to calculate the electronic properties, structural properties, the mechanical, including elasticity, of course, the dielectric part, especially dielectric part is related to our spectroscopy or the optical properties. Then we have the vibrational Raman spectra. And then we go on and look at the thermoelectric properties if you would like to do it. But the question is always, as you know, this is approximation. So what we cannot do, or is not easy to do. And always remember, DFT by definition is governed by the ground state density. But once you excite the system, perturb it through either photon, electric field, or magnetic field, you're going to have excited states. So always we are using the ground state density to treat the excited states. And that's is the questionable, is how to do it. And the results are not as good as the ground state property. So that's a really a drawback. We have now a few more models to treat it, but in principle, we cannot do it. And then we have, of course, the transport property, especially in the insulating system, the results are not as good as one should expect. So this is the first sort of example. We pick up a nitride bulk material. And first question I ask you is, can we simulate a nitride material in different crystal structures? So as we know, the boron nitride is in hexagonal case, and both aluminum and gallium are in woodside. So this is different crystal structures. So you take the structural information, you take the guess, and you find the minimum ground state energy and density. And from there, we see is the lattice constants are pretty reasonable. And now they are within a few percentage of the experimental values. So it's very, very well defined, and we can really determine very well. The nature of the gap, again, is more or less we reproduce it. But there is a problem here, like I said, about calculating the excited state property. So you're going from valence band to conduction band, and the DFT always underestimate the gap. So if I look at the boron nitride, the gap is about 5.2 eV, is almost half of it. ALN, again, is a little better, but is underestimation. And GAN is the same thing. So when someone talks about the band gap coming from DFT, always remember is going to be underestimated. And we have to use a sort of, I call the ad hoc arrangements to fix the band gap or improve the band gap values. So this is sort of a slide, and just came out paper last year. And you can see what they're doing is they are picking up a variety of semiconductors and insulators. And you can see the series of functional forms. There are at least hundreds are out there. They're classified in LDA, GGA, hybrid, or meta GGA. But the key thing is if I look at the mean absolute error and mean absolute percentage error. Look at here. The dots are LDA, or if you look at the triangles are GGAs. They are way up here. So the underestimation of the gap is pretty high, about 1.1 EV. But if you go to so-called the hybrid functional forms, there is a error. It's about 0.5 EV, or about 25% or 30%, but is much better than what we have in LDA or GGA case. So then comes out is some of the functional forms are the accurate functional forms for these calculations. It doesn't mean they provide the accurate band gap, but they are much better than this part of the graph. So, like we talked about, this ionic bond, covalent bond, but what happens when we have this called the graphene or carbon-based structure, where the flexibility of electronic cloud in, say, graphene sort of induces a weaker interaction. And we refer to called van der Waals type interaction. And if you remember what we taught in the solid state physics, how come xenon is stable as a solid? Because shells are filled. So there's no transfer of electrons or no sharing of electrons. So xenon, neon, or krypton, all these noble gases, they are stable in a solid form because they have this electronic cloud, which is flexible. And the interaction of the xenon atom induces this van der Waal type of interactions, which provides the stability in a solid crystalline state. So there are some expressions to treat this van der Waal interactions, but this also gives you an idea about both the limitations of the DFT model. So I pick up a sort of a dimer, is a two-molecule system, benzene, passivated with hydrogens. And as you know, we are in the plane, and the carbon has px, py in plane, but there is a pz out of plane. So pz coming out of this way, from here is this way. So this pi electronic cloud interacts with each other through van der Waal type of interactions. So if we calculate the binding energy of the system, means I'm varying the distance, which is on x-axis, with the energy. So look at the GGA part, which is in the dashed line. And what we see is the system, if we treat the DFT in GGA functional form, it predicts it is not stable at all. But if you move down and then use the van der Waal interaction term, it does show a binding, which is pretty small. Means we're talking about here kilocal per mole. So a few kilocal per mole binding does come up if we introduce a realistic or the physically correct functional form. So you have to be very careful that which system you have, and then from educated guess, you choose your functional forms. So I give another example, graphite. Graphite, as you know, is a layered graphene material where the layer sort of carbon atoms. And if you compare the binding energy, comes out about 17 MeV in LD approximation, but experiment is about 52 eV. But if I introduce so-called van der Waal type functional form, which sort of the interaction it represents, the binding energy is improved by quite a bit. So for carbon-based systems, the message is one has to have the van der Waal type of interaction included in calculations. So let's pick up an example about the oxides. These are the bulk oxide. And you can see is sort of a interplay between simulation or theory and experiment. And this we did a few years ago, work with a group at National Physical Lab, Delhi, through a CSIR grant. So we are looking at the two materials, the gallium oxide, and then once we know how well we can predict the properties, we can move to the complex one, is a gadolinium calcium zinc oxide. Most of us know gallium oxide is a well-known, the UV transparent conducting oxide, and the reason is gap is pretty high, and is being used in flat panel displays, solar cells, and the laser lithography as a thin film of the material. And this gadolinium calcium zinc oxide, if you do with a uranium-2+, is a well-known or the proposed candidate material for red-emitting phosphors. So way back when we looked into gallium oxide, we realized that nobody has looked into the material, and only the people have studied the structural property. They don't know much about the optical response of the material. So first question we asked is, if we apply, what is the ground state of this material? And if we apply the pressure, does a phase transition occur? If it occurs, in what kind of structure is it going to have? What kind of value of that high pressure value we need to make this transition to occur? So we have again the model. I'll skip the model part and show you the result. So here what we had done, you can see we sort of plotted the energy versus volume curve of a given crystal. So we know that the gallium oxide has this structure, and we then take the ground state or equilibrium volume, and then either we expand it or compress it. So that's why we had change in volume here, you can see. And each volume, we calculate the energy. So this beta phase, you can see, is nicely comes out and giving us about, this is the equilibrium volume, and this is the energy. Now what we do is we pick up a hexagonal phase. And this again is an educated guess that beta, if you apply the pressure, it's going to squeeze in and form an alpha phase. So our task is, if it forms alpha phase, what the pressure is going to be. How much pressure do we need to squeeze the material? So we take this structure and again, we calculate the energy versus volume curve. And interestingly, if you see these energy curves, they cross at this point. And if you take the tangent of this crossing point, then this tangent is going to, slope of the tangent is going to give you the pressure. That we start from here, we start compressing the material, it goes up, and then now at this point, you can see it's not going to go up because this is a higher in energy, but rather switch to or move to the alpha phase. So that's why the tangent of this crossing point and slope of the tangent gives us the pressure, which is about 10 GPa. So that's good. We know is achievable, and we have both alpha and beta phase. Now the question comes in is, let's look into the experimental values, which is known for the beta phase and not for the alpha phase. The later sort of numbers came in, and you can see the results are pretty good. You know, as we're talking about, the angle here is within a few tenths of degrees, and same thing here in the few tenths of angstrom. We have the lattice constant for beta phase. And then again, you can get into the so-called the fractional coordinates, which the crystallographers, they love, and you can compare and they come out nice. Now the thing is let's look at the band structure. So what you find is we have the beta phase, which is the ground state, and we have nice localized so-called the oxygen 2s, gallium 3d, and oxygen 2p. So this forms the valence band. And then we have the conduction band. Now, sometimes people ask the question is how come the anions of a given crystal, they are always on top of the valence band? And the answer is simple. Is if you look at the cation tends to be heavier, and the electronic states are going to be attracted by the nuclei, the protons, which are more number of protons. So they tend to be deeper compared to anions, which are shallower. And second thing is also, in every case, anion is the one which controls the response of the system. Because whenever they have called flexible electronic cloud. But the MgO is being formed because magnesium is giving away electron to oxygen. And oxygen is willing to accept the electron because it has a flexible electronic cloud. So no matter what you do, is all the insulating systems or semiconducting systems, which are heterogeneous, the valence band is going to be formed by the anions. And then you calculate the numbers, what the location is, and these numbers effective mass. And these numbers indeed are helpful to XPS, where they calculate the core level spectroscopy. And you can compare, for GA 3D band, the location, it comes out to be within the error bar of experiment. Look at the gap, and the thing is what is the direct gap? What is the indirect gap? You can see here is, if I call direct gap, means if I pick up the high symmetry point, top of the valence band, it makes a transition to bottom of the conduction band. If they are at the same symmetry point, we call the gap to direct. But the electron also can go not here, but it make a transition to M level. So this becomes a indirect band gap. Then you can calculate the values also in this sense. So let's look at the optical properties, which is important. And these are some of the equations, but I will skip it. But we can calculate the dielectric constant function. And once you know the dielectric function, you can easily calculate the reflectivity and then so on. And these are the peaks comes out energy versus the real part and the imaginary part of the dielectric constant. And then from there, epsilon 1 and epsilon 2, you can calculate the reflectance spectra. And you can see this is the beta phase, which is the ground phase. But when it makes a transition, it does show some features which are different from the ground state, which you expect. Because as you squeeze in the material, these cation and ion is going to have a different near neighbor surroundings and different lattice constant. And then you can also calculate the so-called energy loss function and compare with experiments, identifying these peaks. So comes out is indeed, we can simulate the gallium oxide and predict the high pressure phase. But the key thing is comes down to as we move from the beta phase to alpha phase, we do see the differences in both electronic and optical property. And easily you can say this is because of the structural modification in the material. Now, this is again it's pretty good work actually. I liked it. We did a few years ago. Is one of our experimentalist friend came in, and he was looking at the zinc, aluminate, and gallate, and these materials are being used especially as a coating in satellites because they have anti-reflective properties. So when he did the measurements and he looked into the analysis part, and he found that the zinc aluminate band gap, it turns out to be smaller than gallate. And then he said it doesn't make sense because as we know from other materials, as you substitute with the heavier element, the gap should increase because you have a more repulsion. And in this case, he's replacing aluminum by gallium forming this gallate. So we did calculation and we thought, aha, means it's whatever intuition we have, indeed, aluminate gap is higher than the gallate. And then he looked into results. And then we told him is your measurements are in a sense incorrect. Because what happens is this reflectivity measurements, they all depend on the particle size of these polycrystalline samples. So he looked into the particle size of the material and he realized is the aluminate particle size is much smaller than gallate. And that's why it's sort of coming out the results which he was not expecting. So you can see here is a sort of I call the marriage that you have some results, you talk to your simulation person and see if you can find and to understand what is causing either the error, if not, then what is kind of interpretation we can provide. So let's move to complex oxide. So one of our collaborating colleague at NPL, they synthesize the material, but they would like to know actually, can we characterize it? Because they're proposing it to be alternative to well-known European doped yttrium oxide. So we thought, okay, let's, before you do, as you know, from experiment, if you want to do or simulation or any work, you would like to pose the question that what I'm going to do. So the questions we asked is what kind of a structure this complex oxide is. Is it a direct gap material or is it indirect gap material? Or what kind of dielectric constant does it have? Because as we know, the dielectric constant of a given material basically tells us or gives us a clue how well the response is going to be to the external fields. Could be photons, could be electric field. And it all comes down to this flexibility of electronic cloud. So we picked up again the structure, and these structures, as we know, is the form of the units, the GDO7, and then we have CO11. This is GD, and then this is the calcium oxide 11 polyhedra and zinc oxide 5. And when you move to tetragonal, then it's dictated by either calcium O10 or GDO8 because of the squeezing of the lattice. Then the same thing you do. You do the energy versus volume curve, and you see, means these both faces, they cross. So thing is suppose I have a tetragonal face here and orthorhombic face here. So if the energy versus volume curves do not cross, means there will not be any phase transition. This is a simple energy argument that if I start from here, the circle dot, squeeze in the material, and comes is this point, and if there is no other phase is available, I'll keep on going. But if a phase is available, it's preferred to switch gear and come to tetragonal phase rather keep on going. So the crossing of these energy versus volume curves gives us a clue there is bound to have a phase transition from one phase to other. And then you again calculate the properties and compare for both phases where you have the experiment is available and here is a prediction. And as you can see, the orthorhombic phase is a ground state, and you go to high pressure, you squeeze in, it's going to have a smaller volume. And then you predict the crystalline properties. This is the fractional coordinates coming from the structures. And then we come to a band structure. And again, gadolinium is, I call the magnetic system. So we had to do a called spin polarized calculations. And you can see here, look at the order of level, the gadolinium, zinc 3D, 4F, oxygen 2S is sitting here. So you can identify these levels. And this is the top of the valence band. And this is the conduction band. So what we came out is the both phases have a direct energy gap. This is a 2.6 eV. This is 3.28 eV. And again, it makes sense because once you squeeze in the material, you have the higher repulsion. So these valence and conduction band, they sort of repel each other and gives you a higher gap. But interesting thing comes out is indeed the dielectric constant is about 6.2 and 4.7, which again reflects into refractive index. So what's coming out is a lower dielectric constant means the material has a relatively higher flexibility in electronic cloud compared to the higher dielectric constant number. And you can plot these sort of curves, epsilon 1, epsilon 2, which are related to reflectivity, and identify the peaks compared to the band structure. And then easily we can look into either photoelectron spectroscopy or reflectance to understand what kind of transition we are dealing with. So in summary, the thing is, of course, we have these two polymorphs, but the key thing comes down is the 4f orbital of gadolinium induces a strong magnetic spin polarization in the oxide lattice. So that's a sort of a fundamental insight about the role of gadolinium in the host crystal lattice. And again, is what you expect. They are going to have a low dielectric constant because oxygen is being involved in the crystal structure. So there was a good work which we did the NPL, and you can see with theory from simulation models, we did provide and predict the properties and help to characterize the material. So how much time do I have? So it's almost about 50 minutes. So I think I'll wait for the break. But let's open to questions or comments about the bulk or a DFT model or anything. Let's have the feedback. Dr. Naidu, typically you ask questions. Any? I think today is day 4, so everyone's kind of tired. Didn't see you. Morning, I said. Oh, good. Do you want to share? Okay. Doing a little survey. Good. I done this gallium oxide long time ago, and surprisingly, now people have picked up, and it has become really one of the most well-cited paper from our group. In the last few years, we ended up getting about 500 citations. So, Dr. Naidu, the key thing is, as you know, people are doing gallium oxide, but see if you can find your niche, because I noticed people have not looked into the defect part. How does the defect play a role in modifying the properties? Because as we know, the material itself is not perfect. And once you form a thin film or use a polycrystalline materials, there's going to be a lot of defects, a lot of impurities. So see if you can move your direction in that way. The question is from Chintak. It depends on application, and as you know, is if dielectric constant is high, what it reflects is the bonding is very strong. Okay, so this I call these bonding tends to be a rigid bonding. So if you really want to make insulating material, or we call the dielectric material for these devices or for these solar cells, then you have to have a high dielectric constant. But if you want to play reactivity or activity like a photocatalyst, then you would like to have your system to have this flexible electronic cloud which can react. And then you have to have a low dielectric constant. So depending on the application. Does that answer a question? So Dr. Naidu, yeah, so you're looking at the polycrystalline. And as you know, polycrystalline means if you form a pallet, you're going to press it, so you're going to induce a lot of defects. So always, first thing is you have to worry about the particle size. And for pellet, if you want to keep the particle size, then you have to do ball milling to reduce the particle size to make it uniform. So look into see particle size dependence on, say, reflectivity. That's going to tell you something. Or you dope it if you take the pallet. Depends on what you would like to do and what kind of facility you have, access to facilities. So, Dr. Abraham, yes. And since you have interest in nanocomposite, what I do is tomorrow, I think about doing the transport. But tomorrow I'll show you one of the slides where we are looking at the composites. And I presume you're interested in the mechanical property, not the electronic property. So there are ways we can look into, say, carbon nanotube embedded in a polymer. So we had done some work recently to look into the mechanical response of this composite system made of polymer and graphene polymer or carbon nanotube, or could be metal oxide also. If you're looking at the optical properties, that's also possible because it depends on, as you know, how you define your structure or unit cell. Is that okay, Dr. Abraham? But I'll try to get one slide for you tomorrow about the mechanical response. So Dr. Somaya is theory, as you know, is applicable to any system. And the question is, we have to take the complex problem, being a physicist, and see if we can reduce to a simple problem. So it depends what kind of nanofiber you're talking about. So we can pick up a fragment of nanofiber and simulate into DFT theory. And again, when nanofiber you're doing, I presume you're doing the mechanical response. You're trying to look at the elastic moduli. So yes, in principle, we can do it, but depending on what your question is. Any specific question, Dr. Somaya, is what exactly you're looking into it? Is a mechanical property for nanofiber? This is what I don't like about the online thing, is because we do not have conversation one-to-one, but hopefully we'll move to offline case. Good. So nobody's saying, so I think let's take a break. So we meet, what is the next 11? We still have a few minutes. Yes, Dr. Naidu, any question? Good. So you need to have a really good X-ray diffraction apparatus, and you can look into phase transition. But my feeling is I used to be experimentalist, not anymore. But annealing, what it does, it induces the defects, because you're taking the pellet and you're warming up to 700, 800, or 1200 degrees Celsius. Until you do under argon pressure. But 800 degrees Celsius, I do not think you can see phase transition, because this is oxide and it's a very high melting point. But definitely you can look into the effect of annealing temperature on both the diffraction through, or if you have access to optical reflectivity experiments. We shine the UV lamp and look at if you have the monochromator, look at the either absorption or emission with respect to temperature. So let me see our calendar. So 11:30. So let's meet now at 11:45. So we take 20-minute break. And what I do, I'll switch to. Okay. Please share the paper and then we can talk more. Either today in the later, if not, then tomorrow definitely. Good. So let's take a break, have some caffeine, and we'll meet at 11:45, and I'll talk about the 2D materials. Okay, let's start the part two today's lectures. So this is a slide is about graphene, just to remind you what exactly we are looking at. That is simply a monolayer of carbon hexagons, and what they have is sp2 bonded system, where we have the sigma bond around the plane, but when the pi electrons are coming out of the plane, and because of the nature of the bonding and structural arrangements, if I look at the band gap, band structure of the material, so this is the valence band, this is the conduction band, and what you find is there's a gap between certain points, but also at certain points they touch each other, and that's referred is called Dirac cones. And then graphene is referred as a zero band gap material. And because high symmetry points, some of the points they have the zero gap. And because of, again, the nature of the curvature of these bands, as you remember, we can calculate the effective mass. And from there, you can see the electron mobility is extremely high. It's what we call ultra high in plane, not out of the plane. So because of the mobility, people thought, okay, let's make the devices, and this is again is a both SEM and NTM, and what you have is that these are sort of coming out the contacts, and then you have the graphene is sitting here in between, and this tells you again the cartoon is you have the substrate and the insulator, so that the electrons or holes cannot leak out. Then you have the sample, and then you have these two contacts. So the question is, this is fine, but typically, if you are a device engineer or electrical engineer, you always look to fabricate called field effect transistors. So this is a little cartoon which tells you what exactly FET is, if you don't remember. So this is again is we have a simple diode-like characteristics here. You have source, drain, contacts. You have channel or material. You have insulating layer, and then you have substrate. So what it does is in transistor you have also the gate arm. You can apply the voltage. Source and drain is a diode-like behavior, and gate is you can apply the voltage through the gate arm. So what it does, it gives you another flexibility by modulating the current going through the system. So what we have is you have the current voltage characteristics, and by changing the value of the gate voltage, you can have again the different values of the current for a given voltage. But one of the necessary requirement for material to be used in FETs is they should have finite band gap. You have to have a semiconductor, then only you can manipulate the gate voltage to modulate the current. But the graphene is a zero gap material, so the question we ask that can we induce the gap, but without changing the mobility? Because this is really, if you want to move forward, we have to have the gap, but at the same time, very high mobility. So people thought, okay, let's do it. So the first sort of attempt made by take a bilayer of graphene and you apply the electric field. So you can see this is a pristine bilayer on left, and you can see there is no gap here. But once you apply the electric field, it's gated, you can see the small gap opens up. So that's a good news, that if you want to make FETs out of the graphene, you have to use two layers and you apply the electric field to induce the gap. So the first question is, what exactly is happening when I apply the electric field? So if I take, in the absence of electric field, these graphene layers are sitting on top of each other, okay, with some interaction. So this carbon atom on top layer and this carbon atom bottom layer are exactly the same. And once you have a similar nature, electronic nature, is definitely going to behave like a monolayer, although it is a bilayer. But the trick of the trade is, what does the electric field do? That this layer experiences a different electric field than this layer. So carbon atom in my bottom layer is going to have different response compared to the carbon atom at the top layer. So they become dissimilar. Now, dissimilar in sense, not the structure-wise, but the electronic nature. Because of the perturbation, the response is going to be different. So this dissimilarity in electronic nature induces a gap, because now they are two different kinds of carbon atoms, electronically. The response is going to be different. So you talk about the device physicist says, aha, this is a good thing, but it's not easy to make FETs in this architecture. Can do something else. So we thought, okay, can we find a material which is similar to carbon? And we realize is there is a material called boron nitride. Both are sp2 hybridized hexagonal network. But the boron nitride is, as you can see, is electrical insulating material. It has a gap. Though graphene has the zero gap material. And the reason is the bonding is different. Here, boron nitride carries a called semi-ionic bonding, because if you're a chemist, you know boron is really electron hungry. So it easily can either donate electron or accept electron. Same with the nitrogen. So the boron nitride has become semi-ionic and a covalent material, which is not the case with graphene. So, but they are structurally similar, because if you see in the periodic table, carbon is group 4, boron is group 3, and nitrogen group 5. So structurally, they become very, very similar. And then we looked around and thought, aha, people have started making these boron nitride monolayers. And you can see here is this sort of the graph shows is there is a monolayer, there is a bilayer, there is a trilayer, and also the quad layer of boron nitride system. So idea came in as, why don't we use the heterostructure and see if we can induce the gap. So advantage what we have is they are structurally similar, so it's not going to be a significant lattice mismatch. Mismatch is going to be very, very small. And this is, the graphene is zero gap. This has some gap. And it also has a boron nitride, is a semi-ionic. So if you remember, the aim is to induce a dissimilarity in the carbon lattice about the carbon atoms. The electronic response is going to be different. So instead of applying the electric field, we are bringing a boron nitride monolayer. So carbon in the bottom layer is going to see boron, and the other carbon letter is going to see nitrogen. And boron nitrogen has a different electronic structure. So expectation is this different electronic structure. So these two carbon atoms are going to be dissimilar in terms of the electronic response, and then we are going to have a band gap in the material. So what you do is you bring in, and this is a typical, the chemist language called the A is stacked, where they are top of each other. And if they're slightly displaced, as in this case, called the AB type of Bernal stacking. So you play around the configuration. But before I do it, I really want to show you uh, the model parameters we use for simulation. Talked about exchange coercion function. So here, simply we are calculating the energy with respect to the distance between graphene and boron nitride. And you can see the distance varies a lot depending on the case. Even for GGA case, you can see it's really very, very shallow with a very, very small binding energy. But once I induce the van der Waals type of interaction in black, you can see we have a reasonable value of the binding energy. So like I said earlier, the graphene or carbon-based systems, we had to have the van der Waals type of term in our DFT calculations. So you do it, you find the configuration and look at now the band structure. So as you know, before we do, we had to have an either experiment or a theory we had to call a reference case. So here the reference case is boron nitride bilayer. So if I take a monolayer, bilayer, you can see more or less same, and this mimics whatever the band is in the monolayer case. This is our graphene, and you can see these are the high symmetry points, K point, where it has a zero gap, otherwise it's a gap. And if I bring in this graphene and boron nitride in this monolayer, you can see it sort of mimics the graphene case. So it means still we have a kind of a zero gap material. So when I saw this curve, I thought, aha, it doesn't make sense. So I asked one of my students to zoom in and see. Can we see a small gap opening? And say, aha, indeed, there is a very, very small gap opening in the heterostructure of graphene boron nitride. So we thought, okay, is it due to the dissimilarity in the electronic structure? And you can see here is indeed there's an inhomogeneous charge distribution. This is a boron nitride, and I said earlier is a semi-ionic covalent material. So you have a nice localized distribution, but because the ionicity you can see is not a spherical, but is a distorted towards the bound center. And this is our graphene, which is a more or less a homogeneous electron density. So when they are on top of each other, these carbon atoms are going to feel either nitrogen or the boron charge density, which is different. And that's why we have the gap opening, which simply comes out to be inhomogeneous charge distribution. So far, so good. But again, you want to ask the question is how can we verify it? If there is an inhomogeneity in the distribution, can we verify it? So always you think of the experiment, I call computer experiment, that we have this spacing. What happens if I reduce the spacing? Means is the layers or atoms in the layers are going to have a stronger interaction, which in turn is going to have a higher degree of inhomogeneous charge distribution. Let's see what happens. And if this is the case, the gap should open more and more. So this is the curve, which shows is the change in the band gap versus the strain, and which I call the strain to be, this is my ground state. And at this point, I'm going to reduce the distance, which is going to increase the inhomogeneous charge distribution. So if you go from 0 to say 10%, this is our reference case. And we see boron nitride, nothing happens. But if you look at the graphene boron nitride, say voila, this is very, very large distribution, increase in the band gap as we reduce the distance between layers. So what it comes out is indeed that we do not have to have electric field simply we bring in a boron nitride monolayer, and because of this inhomogeneity, it really opens up the gap in graphene, although it is small, which is fine. But then definitely the system can be used as a channel material for FETs. So as you know, we had to find some topics for a PhD student. So Xiaoliang, when he did this graphene boron nitride system, I told him, okay, you have a graphene boron nitride bilayer. Let's look into the tri-layer system. So in a sense, you have either graphene, boron nitride, or boron nitride in the middle, you have graphene and graphene, and see what kind of electronic structure or transport properties we can predict. So again, is typical case is what you do is this case is a graphene, boron nitride graphene. You pick up a different stacking patterns and then calculate the total energy of the system, find the structure information, and the same you reverse it. You have now the boron nitride, and graphene is sandwiched, and a different stacking is a Bernera stacking. This is the hexagonal, this is the rhombohedral, and then you calculate the total energy and find that's what we expect from ABA stacked material is a lower in energy. And then you do the binding energy and the distances and other information. But the key thing comes down to is look at the band structure. So what we have is a boron nitride sandwiched between graphene. And you can see here there is no gap. But if I sandwich graphene between boron nitride monolayers, the gap has opened up tremendously. If you remember the bilayer case, the gap opening was very, very small. It's about few hundreds of milli-electron volt. But now we bring in another boron nitride at the other side, and that definitely finds a higher degree of inhomogeneity and gives about now a few tenths of electron volt. So we thought, okay, that's fine. Let's see what happens if you apply the electric field. And if you look at this is a zero field case. And if I apply the field about a half volt per nanometer, which is pretty high, about 10 power 6 volts per meter, you can see these are the lines are red. The gap opens up. Same thing with the other system. So first thing it proves that going from bilayer to tri-layer, indeed our hypothesis about the band gap opening and inhomogeneous charge distribution is correct. So you can do, instead of applying electric field, you can simply bring in a structurally similar material, which is different in electronically. The boron nitride is insulating a semiconductor. And then you do, is a lot of, again, experiments that what happens to the gap if you change the electric field. And then if you look at the case here, this is the bilayer case, and it remains more or less same. If the graphene is sandwiched with boron nitride, is more or less same. But if you look at the boron nitride sandwiched between graphene, you can see there is a modulation of the gap. Starts from 0, it varies and then saturates. And further, if I zoom in, I find this variation to be stacking dependent. So that's a sort of a atomistic details we can extract from our simulation. So the question is, what exactly is happening? Because if you see here, the graphene sandwich between boron nitride is really behaving like a bilayer graphene. If you look at the charge density, and you find is no matter what the stacking is, in this trilayer case, graphene dominates. Okay, you can see they're talking about the pi electrons, the pz electrons. They always dominate, even if you have the boron nitride either in between or outside. So that's the key thing. In these system, which is very, very small, the electronic structure of graphene is going to take over. And simply, like I've been telling you, is dictated by how flexible the electronic cloud is. So, like I said, in a trilayer case, the key sort of result is we have the stacking dependent, the gap which modulates because of the electric field. And then if you go to the other case where graphene and boron nitride, there is no modulation. So in experiment, what you can do if you do the experiment and look at the modulation of the gap with electric field in a trilayer case. And it's not easy to find out what kind of stacking my trilayer is. But the theory is telling is if you have the certain type of modulation, it's going to be either AAA, ABA, or ABC. So in a sense, we are assisting the experimentalists to understand their results about the material's property. So let's look into the other systems. And as an electrical engineer or device physicist, you're always looking for the case where you can tailor the properties. Okay, the whole idea is to have a tunable band gap without modifying the properties of the host material. Okay, so we had done earlier the cases of bilayer or trilayer. Okay, but now if you pick up a, say, monolayer and see we deposit either atom or cluster of atoms or atomic wire and see what kind of results we are going to get it. Can we tailor the band gap? Dr. Naidu, no, graphene is not magnetic. Because if you remember, for a magnetic system, we have to have a difference in spin between spin up and spin down. If there's a net spin in the system, like nickel, where our 3D shell is empty, is half empty, means it is not fully filled, then the electron can have a possibility of going to different electronic states, which giving you the net magnetic moment. But by definition, yeah, graphene, so you know, but you're right, we can convert it. And whole thing is converting out is, can we have a add atom sitting on top of the graphene, or can we substitute it? And I'll show you some of the results that it can be done. So this is the question. So let's change a little bit gear, and I'll talk about, there's another interesting material, transition metal dichalcogeniide called MOS2. And also I look into the very interesting material coming out, is called phosphorine. And then we know that boron nitride is semiconducting, but the idea is if we can dope boron nitride monolayer, can we change the band gap? So in all these cases, our approach is not to modify the host lattice property, but look into the tailoring the electronic property. So this is a MOS2, and you may have seen MOS2 sort of a structure. Is a Uh, in a monolayer, we have the called tri-sublayer. So we have sitting the molybdenum sitting in between and surrounded by two sulfurs. That's why we have MoS2. And it can form, this in a different crystalline forms in a 2D monolayer called trigonal or octahedral, depending on the coordination of MO atom. And this is the interesting thing is this is semiconducting. So people have done some experiments, and this is again is a voltage versus a current, source drain current. And you can see the MoS2, it is semiconducting. So it's going to have very, very low current. This is in a microamp. But once they add these gold nanoparticles, you see the rise is current. So in a sense, they tailored the property of MoS2 by functionalizing it through the gold nanoparticles. So in a similar fashion, Dr. Naidu, we can again induce a magnetization in either graphene or in MoS2 by depositing, say, manganese nanoparticle or a nickel nanoparticle, which are magnetic in nature. So this sort of gives you an example. It can be done. So what we thought is as you know, is not easy to make these gold clusters. And then you got to deposit. So there's a lot of complexity in the fabrication process. So we thought, what about instead of a nanoparticle, we look into the atomic wires and how they're going to change it. So yes, Dr. Naidu, any magnetic particle we can incorporate adds called add atom. It's not easy to dope it, but you can functionalize by adding on top of it. It's called decoration. Decorated manganese and nickel particles on the graphene or any monolayer. So you can see here is we can use a sort of a different views. I call XY, YZ, or XZ. But this is our lattice, and we are looking at the nanopart atomic wire on top of the different side called top side. They're sitting exactly on top of the atoms, and then we have so-called the hollow side, where they're sitting, and you can see from here actually. This is the hollow side, and here is the top side. And you can play around and then do different things. And then you basically see what my ground state energy is, and you optimize the configuration, and from there you extract the information about the structure property. So we started with the gold, but as you know, as a physicist, you are interested in the variation of the property. So I asked the student to start with the gold, but again go to the noble metal series, silver and platinum, but copper also is being used as interconnect. So let's look into the copper also. And you can see there is this variation. Gold and silver we know behave more or less same because of the properties. And platinum is a smaller, misses a little more attraction to MoS2, and copper is in between. So you want to see what kind of bonding our system is going to have it. So we have is called the valence band charge density. And when you plot it, going from gold to platinum, so this is our monolayer, MoS2. And these are our atomic wires. So you can see the top of the valence band is dictated by not our substrate, not the monolayer, but atomic wire. So the properties of this system, atomic wire plus monolayer, is dictated by the wave function or electron density of atomic wire. So you can see that serves our purpose, that we don't want to change the structural property of my substrate, but we want to tailor the gap by changing the properties of this, by making sure that the electronic properties are governed by my atomic wires, which comes out to be correct. And then you do density of states. And here you see a very interesting pattern. This is our MOS2 monolayer. This is the Fermi energy. And what we see is there is a gap, which is insulating or semiconducting. But once I add the copper, there's a finite density of states appear at Fermi. Silver is not at the Fermi, but close to Fermi. Gold, again, is moving towards the Fermi. And platinum, indeed, is at the Fermi. So you can see by varying the composition of atomic wire, you can convert a semiconducting material to metallic or half metallic, we call it. The same thing you can see, the band structure. The pristine has a large gap, about 2 eV, 1.5 eV. The copper, this peak shows up. Silver, again, is a much sharper. Gold. Now you can see this is our conduction band. So as we're moving from pristine to copper to silver to gold, this is moving the top of the valence band as well as the conduction band. And that's a platinum, which you can see is totally different in red compared to the other three elements. So the conductance we can calculate, what they call is by crossing of the band at the Fermi is about 2.0. And the platinum turns out to be a semi-metallic because you can see the Fermi energy, some of the valence band or over Fermi energy means they're half occupied. So the information comes out from band structure or density of states. But if you take the information and talk to experimentalists, they say, what does it mean? Can you calculate the current voltage characteristics so that I can see that material, can it be used for device or not? So we thought, okay, let's do it. And this is called tunneling current sort of approach, where you are, if you remember in STM measurements, you have a tip and you are sampling the surface by applying the voltage. So what happens here, that's the key thing here, is when we have positive bias, this current is flowing from tip to substrate, we map out so-called the conduction band. And when we have a negative bias, we go from substrate to tip, and we map out the occupied states. So one has to be really careful to see what kind of bias you are going to apply. So you're probing either the conduction band or valence band. And that's they are theoretical expressions which tells us this current simply is proportional to so-called a local density of states. And you can either probe occupied or valence band or conduction band depending on the bias. That's another cartoon that coming from the model. So we have the tip here, you can see, and the substrate. So we model our tip by a small cluster, and then you have the substrate, and this is the monolayer. Typically, the distance turns out to be about 3 angstrom between monolayer and a substrate. And what we do, we calculate the density of the state of the tip and the monolayer, And the convolution basically provides us the tunneling current. So here's the result. And you can see we're looking at the semiconducting MOS2, and that's a flat between whatever the applied bias go from 0 to plus 0.5 or negative 0.5, which makes sense because it has a gap of about 1.6 eV. So we do not have enough energy to move electron from valence to conduction band. So it gives you a sense of relief that our model elements do predict accurately the reality or the experimental observation. Once we move to silver, the rise in current. The gold, again, you can see the rise in current, but this is all in the positive bias. Negative bias, we are more or less flat. But the very, very interesting picture comes in when we have the platinum. You can see this is what we call is the typical ohmic-like conduction. So results comes out is indeed, once you functionalize these MOS2 with these atomic wires, they are conducting. But for the platinum case, we have a really the semi-metallic behavior, which induces a nice ohmic-like behavior. And from there, like we talked about, you can again have this topographical images depending on negative or a positive bias. So in this positive bias, we are looking at the valence band, and for the negative bias, you can looking at the conduction band. And from here, you can really map out the difference here. This is a very, very conducting. So you can easily see the conduction band here, the states. And for other cases, we can see easily the valence band states. So summary is indeed we have a tuning of the gap as we functionalize the copper, silver, gold, or platinum. And then if you do the estimate images, we can definitely understand or interpret the experimental images. So this is the case. We have done MOS2 with the atomic wire. So this is a deposition of atomic wire on the semiconducting surface, which is much easier to do it. What we thought is let's go further and like Dr. Naidu asked a question about the magnetic elements and can we dope them or can we decorate them? So decorate is very, very easy, and I'll show you. When you dope, it means you are going to replace one of the host lattice atom, which is really requires a lot of energy through the doping. But we thought let's pick up the doped case and look into the boron nitride monolayer and see when can we tailor the electronic property. So when you start this is a boron, this is a nitrogen in the periodic table, and we thought let's pick up the group 4 element. Now this is the simple analogy of, if you remember, the doping of silicon by either N-type dopants or P-type dopants. If you go on the left-hand side of the periodic table, it's going to be P-type, and you go to the right-hand side, it's going to be N-type. Because when nitrogen substitutes silicon, is going to provide the extra electron. In our case, we are picking up the boron nitride as a host lattice. It's reverse. So if silicon goes to boron, boron has 3 electrons, silicon has 4. So silicon is going to provide the N-type doping at the boron side. If I go to the nitrogen side, nitrogen loves to have 5 electrons, but silicon only has 4. So it becomes a P-type doping. So we consider the cases, silicon and boron, silicon and nitrogen. And what we also consider is what happens if two of the silicon atoms replace both boron and nitrogen at the same time. So these are the results. So what you do is you bring in silicon, replacing the boron and nitrogen and boron nitride pair, and then you relax the system. So you calculate the total energy of the system with respect to the relaxation. And once you have the lowest total energy, we say this is the ground state. And in this ground state, you can see, certainly we have the sp3-like hybridization. So silicon sitting at boron or silicon at nitrogen, they come out of the plane. And this distance is about 1.2 or 1.7 angstrom. But if I take the two silicon atom replacing boron and nitrogen, they don't want to come out. They simply to be happy in the in plane. So there is no Z distance here. That's good to know. So what it comes out to is the silicon prefers threefold coordination, no matter it goes to either boron or nitrogen side. But if you take the two silicon replacing boron nitride, two atoms, it really prefers the fourfold coordination. So with the charge density. And what you can see nicely, that the silicon coming out of the boron has really polarized the nearby atoms. And same thing, silicon at nitrogen. All the polarization you can see is slightly different. And boron nitride, silicon replacing boron nitride simply doesn't change at all. I mean, there is slight polarization here, but overall is very, very minimal perturbation in the electronic density. So the band structure. And surprisingly is what we find, if you look at it here, this is the boron nitride monolayer, it has a gap. If you go to silicon nitrogen or silicon boron or silicon and boron nitride, we see these are red dotted lines. For one case, the red dotted line appears. For the other case, they are very, very close to the Fermi energy. You can see. So you can see here is by choosing the site where you would like to dope is going to have a very, very different electronic signature for the dopant system or dope system. And it clearly shows up in the density of states that this is the pristine. There's a gap here. If you look at the silicon at boron, these states show up, not exactly at zero, the Fermi energy, but nearby. For silicon at nitrogen, the states are here, up and down. And for boron nitride, indeed, they are at Fermi. So the message comes out is a doped boron nitride. It is going to have so-called mid-gap states. And their location is side-dependent, going from boron nitrogen to dipair boron nitride. That's good. But again, for a person who's making device, it doesn't mean anything. You know, they said is, can you translate the location of these mid-gap states in terms of the signatures in current and voltage characteristics, IV curve? We thought, let's do it. And we follow the same STM model and look at the current now. And here really is the difference shows up clearly. That if I look at the boron nitride monolayer, which sort of provides a nice agreement with experiment. But if I look at the silicon at boron and silicon and nitrogen, they're totally different behavior. So this is more like ohmic-like conduction compared to what we have for boron. So mid-gap states near Fermi definitely modifies the current voltage characteristics and gives their unique signatures. That's fine, but can we image them? And you can see is where the case is. If I look at the image, silicon at boron, silicon at nitrogen, or silicon at boron nitride side have a different imaging pattern. So the message comes out that the doped semiconducting boron nitride monolayer is going to be conducting. But the degree of conductance depends on the side where our doped atom has gone to. So for experimentalists, it's easy to look at the image. So suppose I find this kind of image. So the results are showing up. If this is the image, then definitely the silicon is preferred to occupy boron side. If this is the image, it's preferred to occupy nitrogen side. So what we have is, we have so-called the fingerprints coming from theory that you can recognize the location of these doped atoms on any given monolayer. So you are seeing the cases of atomic wire, the doped system. And now let me pick up quickly about the atoms on a new material called phosphorine. Or I think this is the last slide. So what I do, I'll pick up these three topics in our last lecture at 2 o'clock, because I think I cannot cover it in the next 3 minutes. So floor is open to questions. So Dr. Naidu, can you see that the modification in electronic properties easily can be projected out to modification in magnetic properties, as long as we have either the add atom or add atom clusters or atomic wires or doping also. But as you are experimenters, you know, doping is not easy compared to simply functionalization.
Session is open for the questions.
Today, Ayushi is quiet. No questions, Ayushi?
Forum is open. I request all the participants to please start their video for a group photo.
Nobody's around? Dr. Saxena is saying is allowed. Yeah. Oh, I see. That's why nobody's around.
Recording in progress. Recording stopped.
Done?
Okay,
Good.
thank you.
So what is the next?
Shall we start by 2 o'clock, sir? Or before that?
No, we stick to the thing. 2 o'clock is
2
fine.
o'clock. Okay.
Because, we have the thing. So let's not change it. So let's meet because you need at least 1 hour to take lunch and take a little, I call a power nap. Siesta. So see you at 2. Thank you. Start. Okay, so let's start the last talk of day 4. And here again is my idea is to give you that there is a word out there which is we call beyond graphene. And again, it comes to the theme of the workshop is about the novel nanomaterials. And as we know, graphene, carbon nanotube have been around for a while. But can we look into the properties or functionality of elemental monolayers or multi-layers beyond graphene? So in our group, we have looked into a lot of other monolayers. But in this talk, I'll focus on this group 5 materials. We did some work on phosphorus and antimony. So we sort of talk about the phosphorus, phosphorine. Monolayer is a phosphorine. To look into the properties, functionality, and if you can shed some light on the degradation process in phosphorine-based devices. And if you have time, then I'll look into the prediction of the monolayer of antimony, which we call antimonine. And that's, I think, is quite successful for us. After giving us the results, the experimental groups have done a fabrication and of devices also. So difference quickly is graphene is a zero gap material. Phosphorine we have advantage is a semiconducting with a low gap or a small gap because if you remember in the last talk we talked about using graphene for the devices, especially the FETs. We have to induce a gap in graphene in order to use it. But phosphorine has a sort of a built-in advantage because it has a gap. And then we look to antimonine, because it is a metallic. And our idea is to see if you can see it's a metallic or semiconductor. And if it's metallic, then can it be used for anti-reflecting coatings? So I'll discuss these two things. So here is I'll start with the so-called the same functionalization of phosphorine. Can we tailor the gap? And then we realize that we have very interesting results about the oxygen. So we look into the material called phosphorine oxide. And then we found out is the phosphorine-based devices, they are not stable, especially in air. So we look into the cause, what exactly the mechanism of this instability is. And then we, after doing the work, we'll move on to antimonine and then show you the present day simulation models have this predictive power where theory guides experiments. And most of the work, again, is a part of thesis of one of my students, Gaoshu Wang, who has done in 3 or 4 years is a lot of work on these materials. So what is phosphorine? And so let's look at the bulk material. And as we know, the phosphorus has a sort of white, red, and black allotropies. And white phosphorus, we know, is quite volatile. Its melting point is about 44, but it really is spontaneously burst into flames. And then we have red phosphorus. Again, is existing in powder, and basically is a non-reactive because of the crystal structure of this thing. But then we also have so-called the black phosphorus. And the black phosphorus is noticed that has a layered structure. So the experimental group, they said, okay, if it's like a graphite, so can we use a Scotch tape method and find or make a phosphorus monolayer, which they refer to phosphorine. So we picked up the black phosphorus and then thought first thing you would like to know is really if you want to exfoliate, what kind of energy you're talking about. And it does seem the exfoliation energy is pretty small. Let me go to full mode. It's about 100 MeV. And then, so it sort of relates to the mechanical or Scotch tape exfoliation that definitely you take a black phosphorus and simply peel it off to have a monolayer form. So once you have the phosphorine, which is a monolayer, you ask the question is what happens if we have the multi-layer system, and can it approach to the bulk value? That's why you sort of verify your modeling elements. So first thing comes out noticeably is definitely is a direct gap material. And as you increase the number of layers from monolayer, which is about 1 EV gap, to kind of a 4 multi-layer, and then you can definitely do the extrapolation to look at the infinite number of layers. And you do find is it does sort of converge to the bulk value of about 0.3 EV. So that's sort of a more or less, it feels better, so that modeling elements can reproduce the bulk-like properties starting from monolayer. So scientists have made the devices. And the reason is here, if you remember, the graphene has a very, very high electron mobility. Phosphorine has a very high hole mobility. And then giving a direct band gap is about 1.5. So with our past experience on MOS2 and graphene, we thought is, can we tailor the gap without changing the mobility, which definitely is going to help us for the field effect transistor devices. Because in graphene, if you remember, we induce a gap about few tenths of EV, and this is still little high. for these devices. So if you can reduce it by functionalizing the surface of graphene, then definitely we can improve the device performance. So how do we start? So we thought let's look at the phosphine is the group 5. And instead of going to column, we thought let's move to the row. From group 3, group 4, 5, 6, and 7. So what we have is starting from boron, which has a S2P1 configuration. And simply we are adding another electron to going to S2P5, which is fluorine. And if we deposit these atoms on the surface and look at how does it influence the band gap or the electronic properties. So in any calculation you want to simulate this functionalization by atoms, first you would like to know where exactly my atom is going to sit on the lattice. What is the preferred adsorbed site is going to happen. So the trick of the trade is you look at the phosphorine monolayer host lattice and see what the sites are available for adsorption. So you can have a top site, you can have a bridge site in between, top, bridge, and then also have a ring site is middle of the ring. So we do the total energy calculation of this atom, the boron, carbon, nitrogen, oxygen, or phosphorus, fluorine, and you look at the top side, the energy profile, the bridge site energy profile, and ring site of energy profile. These are the series of calculations. And you plot the curve. And so this you can see here, this is energy versus distance at different sides. Top, T is top, B is bridge, R is ring for every atom. So from here, you can figure what is the lowest total energy configuration. Like for boron, we can find is ring-like site is preferred. But if you go to fluorine, indeed is the top site. So in this way, you can pick up the ground state of these adsorbed atoms on phosphorine and take that ground state to do further analysis. So this is again is a cartoon, it's complete diagram for the ground state. And what you notice here is again is the phosphorine is like a carbon has extra electrons which are dangling out perpendicular to the surface. So when boron comes in, and as we know, boron is a group 3 element, is the electron hungry. It loves to grab electrons. That's the nature of the boron element. So basically, it goes down on this planar surface, sits here, and then forms a sp2-like bond with available phosphorus electrons. But as you move from boron to carbon, you can see now is the add atoms, they don't want to sit in the plane, but they really want to come out of the plane. So boron, carbon more or less in plane, but nitrogen is trying to come out, and then oxygen definitely is out, and fluorine you can see is the dangling sort of a bond formation here, and it doesn't want to sit on plane, rather come out of the plane. So this is also gives a nice sort of a trend that if we go from S2P1 to S2P5, they're going to have different electronic configurations because it's availability of electrons and the way they form the bonds. And then from this thing, you can see, indeed, the boron and carbon are in plane, sort of prefers in plane configuration, but fluorine is really way out, is basically at about 1.8 angstrom in perpendicular to the plane. So once we have the structural configuration, we look into density of states. And here is again is what you expect from elements of semiconducting physics. Whenever you had absorbed atoms in a material, you expect so-called these mid-gap states near Fermi. So boron, carbon, uh, nitrogen, and fluorine to have the mid-gap states near oxygen, near Fermi surface. But surprisingly, is we do not have any mid-gap states for the oxygen. So that's a very, very interesting result that oxygen, the states, they prefer to deepen in valence band rather than coming out of the valence band near Fermi, which is the case for other four elements or four atoms. So we kind of are intrigued by the oxygen's behavior with respect to the phosphorine. So again, like I said, when you talk to experimentally, they say, okay, that's fine, test of states, but you had to look into the called IV characteristics so that they know how does this mid-gap state affect the transport or tunneling characteristics. So we use what in previously did the STM like a simulation step with the tape at distance, and then basically we are scanning the surface, and this is our adsorbed atom. This could be boron, could be oxygen, could be fluorine, and then we have this tunneling characteristics. So this is I on y-axis, and bias is along v-axis, and 0 is our Fermi. So if you remember the positive bias, it explores so-called the valence band, and the negative bias explores the conduction band. So all these sort of elements, atoms, boron, carbon, nitrogen, fluorine, because of the mid-gap states, we see like ohmic-like sort of a conduction. And oxygen is distinctly different from these other four elemental atoms. It has is a sort of a diode-like behavior, which you expect because it does not induce the mid-gap states. So that's good. So results come out is these current shows definitely dependence on the nature of the atom, but oxygen is a distinctly different. So naturally, you ask the question is, if I take the oxygen and simply functionalize the phosphorine instead of a single atom, you simply go, I call is a partial coverage or fully coverage of these atoms on phosphorine and see what happens. So we thought, okay, let's look at the behavior of oxygen, and you can see in this little animation that is coming out and trying to form bonds with the phosphorus atoms, and ultimately it settles down. And then from there, the location you can easily calculate is called energy surface, and how much energy is required to move these oxygen atoms in the lattice from one side to other side. And this is about a reasonable sort of a 1.3 volt from going from P3 to P2, or P2 to P1 is about 0.3 eV. So which is a reasonable sort of values. So like I said, now is we are moving from a single atom absorption, simply fully covered, the surface fully covered with oxygen. So we are moving from phosphorine, which is here on the left, to what we call phosphorine oxide. So you functionalize, you optimize, and you arrive at the sort of a ground state of a phosphorine oxide with about 1.5 angstrom distance between oxygen and then phosphorus atom. And some angles, this information is there. And key thing again is you can see, because of the absorption of the bond formation of phosphorus with oxygen, the changes in the phosphorine lattice is minimal. And in the pristine case, the distance about 2.3 angstrom, it of course is going to change, but it is not much. The angle you can see also is about 103.7 degree, which is about 121 degree between these phosphorus atom in the monolayer. So the message is oxygen definitely gets absorbed on phosphorine, but in the same time, it does not distort the phosphorin lattice significantly. So from here, then you go and then look at the how stable the phosphorine oxide lattice is. And for this, what we do is we do the so-called phonon calculations. So phonon calculation basically provides that if you do not have any the negative frequency, this is the frequency, and this is the space, high symmetry points. So this is not the electronic band structure, but this is the dispersion relationship of phonons. So this is different. So you see is indeed we have the acoustic mode coming out, but also we have the optical mode. And this is at high frequency, about 1,000 or 1,200 centimeter inverse. And what we expect, again, is due to the stretching phosphorus-oxygen bond, which tends to be pretty strong. That's why such a high value of these branches. So what we say is, indeed, oxygen sort of comes in and forms its oxide, which is pretty robust, stable. So that's the sort of stability of the system. And we looked into now the band structure. And as you expect, when single atom sort of it does not change the band nature of the phosphorine, we don't expect also the oxide to have a different band structure. So it again comes down to a red band gap. Of course, the value is going to be different. And then you can look into the nature of the top of the valence band. You can see these are the, again, px or py orbitals, which is forming a bond. And then in conduction band, which is an unoccupied state, we have these dangling bonds, which is sort of forms the conduction band. So that's good. So we have a add atom. We have a fully covered phosphorine with oxygen oxide. And you ask the question is, what happens if I reduce the coverage of the oxygen? So my phosphorine oxide is going to be 100% coverage. If I pick up half, it's going to be 50%, 25%, and is about 13%. So in this sense, you have the 0% coverage means a phosphorine monolayer. You have 100% phosphorine oxide, and you're trying to see the trend. What happens if I vary the coverage? So again, these are the phonon calculations, the frequency versus K space, and you find is they are more or less pretty stable. And as you move from 100% to 50% to 25 or 12%, there's a shift in this optical branch, which represents phosphorus-oxygen bond, which you expect because now, in this case, we have a fewer oxygens compared to 50 or 100%. The same thing you find in terms of the band gap. Nothing changes much except the band gap values. So let's see what happens to the band gap. And here is a very interesting curve. What I said, find the so-called the direct gap or indirect gap. So direct gap is defined is the energy gap between top of the valence band and bottom of the conduction band at the same symmetry point. So for this case, this is our direct gap. But at the same time, electron, when excited, instead of going here, with the high energy, it can go to this side. So when the symmetry points are different for top of the valence band or bottom of the conduction band, we call this gap to be indirect. So direct is the same symmetry point, indirect is a different symmetry points. So you plot this in nature. So if you look at the black, this is my without oxygen. We increase the coverage, 25%, 50%, and then is fully oxidized. So what you find is indeed, you can see the partially occupied, partial coverage of oxygen and phosphorus gives a very, very high value of band gap related to either bare or fully oxidized. But at the same time, if I look at the indirect band gap, so again, it's bare, increasing the surface coverage, and for fully oxidized is about 1.3 eV. So you can see is the alternative nature of the gap is for pristine is a direct gap material. Same with the fully oxidized pristine is a direct is a minimum energy gap. But in between, we have transitioned from this direct to indirect, which is a very, very useful information for applications, making devices. Same thing you do then, okay, we have the gap nature. Let's look at the tunneling current. And we are using the same simulation tip. We bring in a tip on the surface and scan the surface to look at the current versus the voltage. And what you see here is this is the phosphorine, black. It has a gap, so you expect it to be diode-like behavior. And for all the other cases also, you expect a similar behavior. It's near zero. It behaves like diode, and then sort of it kicks in the current when you have the higher voltage. And if you look at the image, you can see this is our pristine without oxygen phosphorine. You can see the zigzag behavior. And for oxidized, you can see that definitely the oxygen is sitting on top of the phosphorus atom. So what comes out to is like phosphorine, the oxygen functionalized phosphorine is a direct gap material, and you can tune the band gap by the partial coverage and also by applying the either electric field or a strain, which I have not shown you the results, but we have seen it. You can tailor it. Partially functionalized has an indirect band gap, which is a minimum energy gap. And the tunneling current, of course, shows the dependence on the degree of functionalization going from 13, 25, 50, 100% phosphorine. So that's an interesting result. And that the oxygen doesn't do anything to electronic structure of phosphorine. And the oxide is either the fully functionalized or partially functionalized is stable. So what we come out with our conclusion that phosphorine in oxygen atmosphere is robust, both in terms of the stability and electronic properties. But if you look at the literature, what experiments have shown that phosphorine-based devices are unstable in air. And this is again sort of SEM graph that this is a phosphorine-based device as fabricated. Within 30 minutes, nothing happens. But after about an hour, you can see start having these holes. And definitely within a day, is a lot of holes, they show up. So you can see as fabricated and after a day, definitely device performance is going to degrade. It's not going to be stable. And if you further investigate it, so this is, if you remember, we use Raman spectroscopy to understand the nature of the bonds between the atoms in a given solid. So if I look at the substrate, it's a nice peak, Raman shift. Then we have the as grown. This should be 24 hours. This is again is coming out is as fabricated. There are hardly any peaks in this region, but within 24 hours, you can see a lot of peaks show up because of the defects or holes in the lattice. So this sort of confirms that this phosphorus-oxygen bond is being broken, giving rise to these additional peaks. So the question is now, what is going on? Because oxygen is fine. So So as you know, of course, air has a lot of different components, but dominated by either oxygen or moisture, H2O. So we thought let's focus on these two dominant the gas molecules rather than nitrogen and other molecules. So what do you do is you say, okay, let's see, I've done the oxygen interacting with phosphorine. Let's see what happens with the H2O molecule. So we bring in the H2O in different directions and find that at the equilibrium configuration, indeed, water has a very, very small binding energy. It's a few tenths of electron volt. So that sort of tells you it could be the monolayer is hydrophobic, not hydrophilic, but it doesn't like water, as such. So let's do further investigate. And you can see here, this is again is the animation. Instead of a one molecule, a lot of water molecules coming in, and simply they're not sticking to the surface. If you remember, for the oxygen, they come out and they really sit down on the surface and form a bond. But H2O simply floats around. So that again tells us, indeed, water and phosphorine, they don't like each other. And it appears to be a hydrophobic material. And this is again the snapshot that shows there is no direct reaction of water molecules, phosphorine. So the two things is, so what we had done, we had taken the oxygen with the phosphorine, and we found is pretty stable. It's robust. And if I take the water only, water doesn't like it. So the question comes in, what exactly is going on for the aging process? What happens? So what we know is acting with O2, they form the oxide, which is fairly stable. And directly, phosphorine doesn't want to interact with H2O. So then our hypothesis was, this could be the two-step process, that in air, we have both oxygen and water. So instead of having a direct reaction of either oxygen or water, first it forms an oxide, and then this oxide reacts with water to give you this phosphorus acid, which creates this defective structure on the surface. So what you do, you calculate the energies of the reaction. And indeed, this is the case that if you form the phosphorine with water and an oxygen in a two-step process, 1 and 2, the energy definitely is gained a lot. So what it comes out to is our sort of explanation that phosphorine degrades in air. That's experimental fact. But the mechanism is first is going to get oxidized, and then the oxidized lattice reacts with H2O to initiate the process. So people have read our paper, and what they had done is what we proposed in our paper, that if you want to sort of make sure device is pretty robust, simply you coat the phosphorine to prevent degradation in the device. And see, this happens. So the paper came out, and they have done again is a AFM characterization, and you can see after about 10 days, when the sample is treated with one of the organic solvent, nothing happens. So you feel good is indeed the theoretical explanation or interpretation of the process sort of feedback loop to experiment, and you can sort of improve the device performance. So this is sort of summarizes that the tailoring of the gap is possible, but when you use oxygen, is pretty robust, but also at the same time, it does not like the water, the hydrophobic, but the mechanism is a complex, it's a two-step process. First gets oxidized, and of course then reacts with water to form the acid, phosphorus acid. So this is all about the phosphorine, and see how much time I have. So about 10 minutes. So I'll show you is indeed we have this predictive power of a simulation method to predict the stability of a novel monolayer, which then experimenters can fabricate it. So like I said earlier, is we are looking at to the group 5 elemental monolayer. After looking at phosphorine, we thought let's do the antimony. And arsenic, we definitely avoided it because we expect arsenic to behave like a phosphorus because they are very similar in nature in terms of the valence electron configuration. And if you look at also the history, is a gallium phosphide is more similar to gallium arsenide. So that let's take a jump and look into the antimony. So what you do is here, so you take the antimony, and now is, remember, we do not have any guidance from experimentalists. So we had to come up with the structures which antimony monolayer can have. And that's an educated guess. So there's a nomenclature. I'm not going to go in detail, but you can look in called alpha. You can see this is similar to phosphorine. Then you have beta, gamma, or delta. So this is a side view, and you can see the difference in this structural configuration. So once you pick up these configurations, and this is your educated guess, now you do the total energy calculation and find out what is the ground state of these monolayers from alpha, beta, gamma, and delta. But at the same time, you would like to see if they are stable or not. So for this, you do the phonon calculation. Look at the stability of the system. So step is a ground state calculation, then do a phonon calculation. And if it does not have any imaginary frequencies, because if you know any structure has an imaginary frequency, it's not going to be stable. So you always look for the frequencies, we are real. And once we know, then you can filter out and then calculate the electronic properties. So we had done the ground state, and then with the phonon calculations. So the frequency versus your symmetry points. And what you realize here is both alpha and beta do not have any negative frequencies. But if you look at the gamma and delta, there's this dip between X gamma direction where it becomes a negative. And of course, delta has a lot of negative frequencies. So definitely we can rule out the possibility of formation of gamma and delta and focus on alpha and beta form. So this is like a filtering process. You pick up any elemental monolayer if you don't have any experimental information. You sort of sample the lot of structural configuration coming from your educated guess of the structures, crystal structures, and then do the phonon calculation. And then you rule out the configurations which have in negative frequencies. Good, so we have now two sort of alpha and beta forms. So what you do is you have the monolayer. Now you would like to see what happens if you have the bilayer, trilayer, or quad layer. So basically you are looking at the prohibition effect starting from a very, very thin sample to a thick sample. And here you see indeed this antimony, the monolayer. If I pick up the alpha, it has a gap. Okay, although minimum gap is called indirect because it's not at the direct symmetry point. But as you move forward, what you find is this one of the conduction branch is basically coming down and crossing the Fermi surface. So what it tells us is bilayer or trilayer are going to have a metallic-like nature related to monolayer. So the results comes out that indeed the antimony is so peculiar that it does show the layer dependent on the band gap. So band gap is dependent on how thick the sample is. And that's a very, very key sort of a conclusion coming out of this work, which you have not seen in other graphene or boron nitride or other cases where you increase the layer, but the band gap remains more or less same. Here we are going from semiconducting to metallic. So we had done it, we published, of course, and in a year, we saw a paper which came out about the fabrication of these antimony, where they used a epitaxial approach to grow these monolayers of, or the flakes. You can see here triangular or the sheet in about a nanometer width of this material called antimony. So this feels good, is someone is sort of reading your predicted results and trying out to make these novel materials. Because ultimately in a device, we had to have help from experimentalists to fabricate the material or synthesize the material so it can be used for other applications. And then later on came out is indeed one can sort of make so-called these MOSFETs sort of based on the antimony monolayer. So you can see these are the contacts left and right, and this is the monolayer of antimony. So I hope in our last 3 talks, I have given you a glimpse or try to convince you that indeed simulation and theory has become a very, very powerful tool to provide the reliable and accurate results. And again, like I said, initially we had to judge our model elements on the given sort of where the experimental results are available to validify the model elements. And once we have the confidence, I think we can go on and predict the properties or the novel material, stability of the novel materials. Good. So I think I'm done. And we have another 5 minutes for discussion. So my plan for tomorrow is, I think, is, if I remember, Dr. Somaya asked about the nanofibers and composites. So I'll give you the glimpse of what can be done there. And so far we talked about the electronic and optical properties. But tomorrow I'll pick up and then at least for 10 minutes, I'll talk about the mechanical properties. How can we get the information about the mechanical response of the material from the DFT methods? And then I'll talk about the transport, exactly how can we calculate. So here we used is called STM-like setup, where the tip sort of coming in and calculating the tunneling current. But if you are experimentally say, this is not the device configuration, device architecture. For a given device, if you want to use a photovoltaic, you have to have the contacts, giving source and drain, and the gate voltage. So I'll show you some of the results on the device configuration, how to calculate the transport, and trying to convince you that at a nano scale, the interface between your channel material or the monolayer and the contact becomes very, very important. And it takes over even the properties of the material. So for experimentalists, they had to be careful how thin the sample is. Thinner the sample, interface takes over. And if you have a little thicker sample, then of course the materials properties take over. Sure, Dr. Somesh will do it tomorrow. Any other questions, comments? So I think, where is Dr. Bhavna? So today is, thank you, Dr. Naidu. Dr. Bhavna is not here, but I think she's going to announce that she's around. So I'll let her announce the good decision. Oh, you're going to announce it? Yeah. Oh, go ahead. Go ahead, Arya. So we have a very good student volunteer, and she's going to announce about the homework.
Yeah.
I hope you talk about the homework.
Yes, sir. Thank you so much, sir, for the elaborate talk. And the chat box is open for everyone if you have any doubts. We'll just share the homework slide in a second. All right, so for today, we don't have any homework for all those who attended the sessions till date. And and we'll have the next session starting at 3:15 today, which is a tutorial session. Hope to see you all soon there.
So, like Arya said, we'll skip the homework today because, something to search. Wow, Dr. Naidu, you are really a very good student. Because, this is not a course, where you go in the class and then do it. And most of you are faculty members or senior students. So I prefer just take it easy. And for me, is even coming to the class is a satisfactory grade, is your pass. But Dr. Naidu, don't worry. You're going to send me a paper today. So let me read the paper and I'll give you an extra assignment tomorrow. Is that okay? And let the other people have a little enjoy. I know it takes a few minutes, but it does take minutes. We are all busy. Yes, go ahead. Yes, please. Yes, please. Can you open the mic for Dr. Naidu?
Hello, good afternoon, sir.
Hello, hello.
Sir, I want to ask, as in the previous lecture you said that अगर हमको कोई मैग्नेटिक या कोई भी सॉर्ट ऑफ डोपिंग अगर हमें करनी है ग्राफिन में, तो वी हैव टू मींस डेकोरेट लाइट, उनके अंदर हम डिफ्यूज नहीं कर सकते हैं.
Agreed.
तो अगर उसे सिर्फ डेकोरेट करेंगे, मतलब अगर सिर्फ उसको लेयर पर रहने देंगे, तो उसका जो इंटरनल प्रॉपर्टी है पर्टिकुलर मटेरियल का, वो तो बिल्कुल भी अफेक्ट नहीं होगा.
Yes.
या मतलब मेरा पॉइंट ये है कि अगर उसे किसी सर्टेन टेम्परेचर पे अगर हम ट्रीट करते हैं तो क्या डिफ्यूजन पॉसिबल है या किसी.
So, Dr. Naidu, yes. What I do is recently we published a paper in Applied Surface Science. I'll send you the link.
Okay, sir.
So, as you know, you've seen the cases. It depends on कि आपके पास what is your concentration of the magnetic atom or cluster. If you're using a very, very small concentration, it's not going to affect at all. So what we had done is we had taken the iron, known iron liya, and we looked into the iron atom, iron cluster. Sorry, this is iron oxide. Iron oxide molecule, iron oxide cluster, and iron oxide thin film. And looking at the effect of its structure or electronic properties, dono ka, on the graphene. And as you expect, FeO or FeO cluster hardly does anything. Simply just go and sits on it and provides you the magnetic moment. But if you have the FeO thin film, usme to it becomes haywire because you have a lot of iron atoms interacting with carbon and it's going to distort the lattice. So, like I showed you, for oxygen case, we have fully functionalized and we have partially functionalized. So it depends on कि how much iron or iron oxide or nickel oxide आप अपने sintering में डाल रहे हैं, annealing में डाल रहे हैं. But I'll send you the link of that paper. And as you know, also, it all depends on temperature. The higher the temperature is going to have much more diffusion. So I call is the trial and error to play around and see. But question ये है कि what kind of magnetic measurements you are going to do? क्या आपके पास facility है? You can open the mic.
Yes, sir. Sir, actually, we are having ion implantation that will be available in Delhi IUSC. And the second one is PLD.
Oh, you're talking about the Delhi Accelerator Center?
Yeah, sir.
Oh, I see. So you go there?
Yeah, once I went. But after that COVID lockdown happens, that's why there's some discontinuity is there. But we are planning for the doing such kind of thing कि implantation का planning है mind में.
That's beautiful. सबसे best part यही है, as you know, ion implantation is very, very specific.
Yes.
You can control by varying the energy. It's going to be on surface or going to go deep down. And depending on the exposure time also, आप concentration उसकी monitor कर सकती हैं.
Exactly. In fact, molybdenum oxide पर हम लोगों ने deposition किया भी था. बट वही जो मैं आपसे पूछ रही थी कि क्या सिर्फ डेकोरेशन वाला प्रोसेस करने से डिफ्यूजन नहीं होगा. एंड हमने तो मतलब पीएलडी की मदद से हमने उसमें डिफ्यूज किया था, तभी भी वो पीक्स एक्सआरडी में हम लोगों को नहीं मिला बिकॉज द कंसंट्रेशन ऑफ डोपेंट इज लिटिल. हाँ, बहुत कम था. तो
पहले तो आपको ये क्वेश्चन करना पड़ेगा कि ऑलवेज यू नो इज एप्लीकेशन क्या करना चाहती हैं आप. आइदर यू डूइंग फंडामेंटल साइंस और यू आर थिंकिंग अबाउट अप्लाइंग टू सम डिवाइसेस. So fundamental science में, as you know, XRD is very, very poor in a sense. Unless until there's a high concentration, is not going to pick it up. And since आपके पास access है IUAC की, to whom do you know, किसके साथ काम करती हैं आप?
अभी सर वहाँ पर त्रिपाठी सर जो है,
त्रिपाठी जी हैं. जी. Because I
also work with IUAC. Ashok sir. Ashokan sir. Second one is Ashokan sir, who is right now working on gallium oxide.
जी.
And Lambert party sir जो है उनके अंडर में.
Director एक पांडे जी हैं, very well.
जी. Actually, I went there for attending a coursework course. जी. So वहाँ पर ये सब चीजें देखा था, तो वहाँ सब देख कर आए, बट उसके बाद कंटिन्यूटी नहीं मिल पाई. बट नाउ वी आर प्लानिंग कि अब उसको हम आयन बीम के लिए अप्लाई करके एंड देन आगे जाएं. तो कुछ ऐसे फर्दर
बेस्ट पार्ट है वहाँ का कि दे हैव रियली स्टेट ऑफ द आर्ट कैरेक्टराइजेशन फैसिलिटी.
Yes, sir. Definitely.
So what they can look into it, not XRD, but we have the electron-based methods, EDS. And तो उससे आपको you can really pinpoint what the concentration of these impurity is in your substrate.
Elemental concentration, right?
Okay, so I'm definitely for you if you can have access to their facilities, and they are very reasonable people. But if you need, give me your email address and other stuff. I can talk to the director Pandeyji.
Definitely, sir. I will. Sure, sir. Sure. I will contact you. आप हैं कहाँ पे? Sir, right now I'm in Madhya Pradesh.
कहाँ पे?
And Ujjain.
अच्छा, उज्जैन में. तो उज्जैन से आप आराम जा सकते.
Yes, sir. So from there, I am flexible to move anywhere in India right now. तो वो एक चीज है कि permission है कि I can go anywhere for work purpose. तो implantation के लिए हम we are
करिए आप and send me email and I'll see. त्रिपाठी जी बताया आपने और एक नाम बताया जो उनका.
अशोकन सर. Yeah.
हाँ, अशोकन. तो उनका भेज दीजिए तो I'll talk to them. I'm going to be there in the first week of March.
Definitely, sir. Definitely.
और जो आपका थोड़ा सा idea है कि exactly what we want to do.
Sure, sir.
If you can just send me one PPT file.
Definitely, sir.
So we can talk about some kind of what kind of measurements I can guide them.
Definitely, sir. Definitely. Sure,
but
sir.
Always remember is I'm coming from the simulation side.
Sure, sir. Actually, so my guide, Dr. Swati Dubey ma'am, is also told me that before doing any sort of experiment, try to do trim and trim softwares so that you have some idea कि क्या result आएगा.
Exactly.
Prediction we should have in our hand कि ये हो सकता है.
So, that's a good approach, really.
Yeah. तो वही चीजें सब अभी कर रही हूँ. That's why questions बहुत
pop up होते हैं. Please, I'm really happy as you know. अगर कोई क्वेश्चन नहीं पूछता है मतलब either you are too bored or nobody understands.
हाँ.
तो उस हिसाब से I'm very happy कि आप पूछ रही हैं. And definitely we'll try to help you out. That's why I'm here, you know, all the way.
Yeah, sir.
And that's the government of India is spending money also to help young generation.
Yes, sir. Sure.
बहुत अच्छा लगा. But आप टच में रहिएगा.
बिल्कुल बिल्कुल sir, definitely.
First week of March में I'm going to be there, so I can talk and we can have some kind of a Zoom session or something.
Sure, sir.
If it needs to be.
Definitely, sir.
ठीक है. चलिए.
Okay, thank you so much once again.
Sure. और कोई? So this is what is 3 o'clock. Up next is 3:15, है ना? Tutorial. Yeah. So again, my suggestion is please see if you can attend the tutorial, because it's really highly relevant to the energy-related applications, and especially the physicist or we have the engineering faculty of students. We don't like chemistry, so this is the time to learn a little bit chemistry, and especially the concept I talked about, over potential. And the electrochemical means is the way for hydrogen fuel economy, you know, if you want to move in the direction, and it's good to know about it. Chaliye fir, so thank you very much. Again, like I said, Arya is no homework today, and we'll see you tomorrow where I cover a little bit nano composites, electron transport, and then what kind of feature we have, and we can have a little more discussion part. Namaskar.
Good afternoon, ma'am. हेलो, गुड आफ्टरनून मैम. नंदिनी मैम, आपको बोल रहा हूँ. आपका म्यूट है शायद. So,
good afternoon to all participants and Dr. Jaidev sir. Now we will start the next session, tutorial session on supercapacitor and electrochemical characterization, which is delivered by Dr. Jaidev. Dr. Jaidev done his PhD from IIT Madras on alternative energy and nanotechnology, and MTech from IIT Kharagpur on solid state physics. His research interests include synthesis of 2D materials such as metal dichalcogenide, graphene, and their application in energy storage and gas sensing devices. He has published his research article in renowned journal and also completed a research project sanctioned under AICT with me. He has more than 100 years of teaching experience. Welcome, Dr. Jaidev, and start your tutorial session on supercapacitor and electrochemical characterization.
thank you, Durgesh ma'am. So, I hope I am audible. Hello, am I audible? Hello, hello. Am I audible? Durgesh ma'am, आपका माइक ऑफ बता रहा है. Yes sir. Okay, thank you. Okay. So, good afternoon, everyone. So, as you can see, the title of my presentation. So, today I'm going to discuss that how a supercapacitor device can be electrochemically analyzed. That means how can we evaluate its performance? Okay. So, performance here, I mean that how can we what is the capacity, charge storage capacity of capacitor, what is the energy density, okay, how it can perform, how can it provide different power density in different condition, and what is how a electrochemical supercapacitor can be modeled electronically. Okay, so before we learn about electrochemical techniques, okay, let me give one brief introduction of supercapacitor and its electrode materials. So, supercapacitor is basically a intermediate device between a capacitor and batteries. So if you see capacitor, okay, capacitor has a very high power density, but it has a very low energy density. Okay, while if you see the batteries, it shows very high energy density, but the power densities are low. Okay, here energy density means what is the capacity or ability of a device to do work. Okay, and power density means how quickly that our device can perform. Okay, sir, any issue? My screen is visible or not? You can on your mic and let me know. Okay, because in chat I'm not able to read. Your screen is not visible. So I had already shared my screen. Durgesh ma'am, hello, hello, hello.
Hello? Hello? Hello?
नहीं डालना है क्यों? ओके hope I am audible now. Okay, so now I was discussing that supercapacitor is basically a intermediate device between a battery, because capacitor generally are known for their high power density, while batteries give very high energy density, but their power only a few hundred under a few hundred cycle life. Your capacitor lifetime can go up to lakhs of cycles. Okay, so this is the construction of a supercapacitor. So electrodes are separated by a separator. Okay, as insulator, one thin sheet. You can use polypropylene sheet or cell guard. So and there's one electrolyte. Okay, so when you apply voltage, okay, so negative ions of the electrode are attracted toward the positive electrode, and negative ion and the positive ions of the electrodes are attracted toward the negative electrode. Okay, so here we have two double layers are formed. Okay, and this double layer act as a capacitor. So you can say this supercapacitor is equivalent to two capacitor connected in series. Okay, and so the electrode are the very important part of this device. So generally carbon based materials are used in these devices. So carbon material generally have very high surface area. The requirement for the electrode material is that it should have a high surface area and should have a good conductivity. So these two qualities are possessed by the carbon materials. So they are the ideal choice of the material of these devices. So carbon materials generally store charge via electric double layer mechanism. So the mechanism just now I explained you, when you apply voltage, the double layer form. So carbon material store charge via this mechanism, and their charge storage capability is very high. Okay, for example, I have given data. The carbon material can store up to 30 to 70 microfarad per centimeter square. Okay, so for example, if my carbon material have a surface area of 1000 meters square per gram. Okay, so theoretically it can store up to 300 to 7 farad per gram, 7 per gram. Okay, that is very high capacity value. So but in generally these are the theoretical value. In practically you achieve only 30 to 40% theoretical capacity. So if you have a 1000 meters square per gram, you can achieve 200 farad per gram. You can expect the device to give at least 200 farad per gram charge capacity. And then so other than carbon material, you can use conducting polymer and transitional metal oxide also as the electrode material. These materials show Faradic charge transfer. Okay, so the charge storage mechanism of these electrodes are quite different than carbon based material. So carbon based material generally stored by electrical double layer mechanism, while these two other electrodes, metal oxide, metal dichalcogenides, conducting polymers, these materials show pseudo capacitance. Okay, pseudo capacitance means when they are the, like example, conducting polymer, they have species which can be oxidized and reduced. Okay, so similarly in transitional metal oxide, if you are using nickel or iron or some other material, other oxide which can have a multiple oxidation state. So when you apply voltage, these transitional metal oxide, these metals can go different oxidation state, and these oxidation reduction happens via Faraday charge transfer mechanism. And this Faraday charge transfer mechanism is dependent on the potential. Okay, so we know capacitance is Q by V. So the charge deliver is dependent on voltage. So then dq upon dv will give you the capacitance. So basically now we can say there's, depending on the charge storage mechanism, supercapacitor are two types: electrical double mechanism, and second one are pseudo capacitors. Similarly, electrolyte is also important part of a supercapacitor. So if you are, because electrolytes generally defines the energy density, okay, because we know the energy density of a capacitor is given by half cv square. So how much voltage we can apply in cell, okay, that depends on your electrolyte. So if you're using water based electrolyte, okay, so then our voltage is limited to only up to 1.2 volt. Okay, if you apply more than 1.2 volts, then our water can decompose. Okay, but this reduces the our energy density, because energy density is half cv square. So v is the applied potential or applies voltage window. Similarly, if you can go with polymer gel electrolytes, you can go with ionic liquids. These gels or electrolytes can provide generally high potential window up to, and with ionic liquids you can go up to 3 or 3.5 volts. Okay, similarly gel electrolyte can give you up to 2 volts. So if you see the energy half cv squared become v, if you multiply v square of 2 it becomes 4, v square of 3 it becomes 9. So you can get very high energy density. But because these gels do not have a very high conductivity, so capacitance value will be low. But finally, since in energy density v appears as a square, so these electrolytes can give you very high energy density compared to water based electrolyte, which generally uses H2SO4 or KOH, okay, in order to get ions in the device. Now, so as I told you, there are three different type of material, okay, which can used as a supercapacitor electric material. So each type of material has its own advantage and disadvantage. For example, if I talk about carbon based material, and they show good conductivity, ideal capacitor like behavior, but because they depend on surface area, so their charge storage capability is very limited. Okay, uh, if we go other side, on pseudocapacitor material which show Faraday charge transfer, like conducting polymer, they can give very high capacitance value, but these capacitance values are not stable. Okay, while you do cycling, you do charge discharge, these the conductivity of conducting polymers go down with time. They slowly they become insulators, and a device to cycle life is reduced very greatly. Okay, so similar thing happen with tungsten metal oxide. Their conductivities are very low. Okay, so the utilization of material is not possible. Effective utilization of this full material, electric material, is not possible when we are using this tungsten metal oxide. Okay, of course the ruthenium oxide is exceptional material, that gives very high capacitance value and ideal capacitor like behavior, but the cost of ruthenium oxide is very high. Okay, so in generally what we do in supercapacitor, we try to fabricate electrodes, okay, which have generally high cycle life, high capacitance, and low cost. Okay, cost is also very important. So I am giving some examples, some before going to how to evaluate a performance of a supercapacitor, how different kind of materials are prepared in supercapacitor. This is example I have prepared during my PhD. So these are the there is the one graphene sheet. Okay, on the top of this graphene sheet I am dispersing these conducting polymers. Okay, so what is the advantage of this type of material? Because if you're using only graphene, then it is capacitance limited. Okay, similarly if you use conducting polymers, for example this particular polymer have very low conductivity, so you are not able to achieve very high capacitance value alone with this material. Okay, And so when we disperse these material, these redox polymer on the graphene sheet, okay, so what happened, graphene sheet act as a conducting path, okay, so this sheet provides a conductivity to these polymers, so its performance increases. Similarly, graphene has high surface area, so it act as support of dispersion of material, so the surface area of this material is also reduced. So in short, we can say these two material can act as a synergically. Okay, synergically means when two things combine, their performance enhanced. So if I use alone polymer or alone graphene compared to these two material, when combined together, there's, because of synergistic effect, they show very high performance. So you can see the images here. These are the images of graphene polymer composite. So in order to get the better efficiency material, you can vary the performance, you can vary the fraction of the polymer in the composite. Okay, so for example, I have made here is PG12. Okay, so PG12 means polymer to graphene ratio is 1:2. PG11 means the polymer to graphene ratio 1:1. So in order to optimize the performance, I have varied these fraction of polymer in the graphene sheet. Okay, so these are the example of binary composite. You can also prepare ternary composites. Ternary composite means, as I told you in the beginning, that ruthenium oxide is the exceptional material for supercapacitor. Okay, but it is a rare, a very costly metal oxide. So this is not feasible. This is not feasible for market. Okay, so what I try to do in this product, I try to reduce the loading of ruthenium oxide. Okay, ruthenium oxide can give you up to 400 to 500 farad per gram capacitance value. So I try to achieve similar kind of values using low amount of ruthenium oxide. So I have made this ternary composite where we have graphene, we have polymer, and we have these metal oxides, ruthenium oxides, and I have prepared ternary composites. Okay, and I compare this performance by binary composites. Okay, so this is a graphene ruthenium oxide, a binary composite. Okay, but when I use this one, I did not see very high increase in the capacitance value, and because the loading is very high, so these binary, the cost of this binary composite is very high. Okay, so what I did now, I have prepared a ternary composites. Okay, so by making ternary composite, I have reduced the loading of this ruthenium oxide, and when I measured the performance of the cell, we are getting almost similar value which we can get alone with ruthenium oxide. So you can see when I'm changing the composition, I am reducing the loading of this ruthenium oxides. Okay, so this is the two method, and there's one more method. Other than preparing new materials like metal chalcogenides, if you want to improve the efficiency of your carbon material, you can dope these carbon material with heteroatoms. Okay, heteroatoms with like fluorine, nitrogen. So when you dope these carbon matrix with these heteroatoms, okay, these heteroatom can give you pseudo capacitance. Okay, so pseudo capacitance is generally very high in comparison to electric double capacitance, so it can greatly enhance your performance of your material. So for example, one there's strategy, you can directly take conducting polymers. Okay, and these conducting polymers you can carbonize, and you can do activation. So when you do activation, what will happen, the surface area of these material will increase. Okay, because capacitance depend on surface area. Okay, of course, when you do heat treatment, so many pores are created, defects are created, that will reduce your conductivity. Okay, but in final, when we check the performance of this material, because of enhanced surface area, okay, the capacitance values are capacitance values are increased. And similarly, in conducting polymers also, and they show conductivity only when they are in electrolyte. In general, their conductivity is also very low. Okay, so when we do heat treatment, okay, so because of heat treatment, we get sp2 carbons, and this is sp2 carbons, they give very good conductivity to this carbon based materials. So these are the some strategies. And so you can see at surface area, whenever we are measuring any capacitance of carbon material, we need two things. One thing is surface area, and surface area can be measured by BET. Another thing is conductivity. Okay, so you can see when we are using pure polymer, the pure polymer surface area is very low. Okay, and their conductivity is also very less. Okay, so when we do heat treatment, my surface area is increased and my conductivity is also improved. Okay, compared to the bare polymers. Okay, so this gave me enhanced performance of these electrode when we use them in supercapacitors. Okay, now I come to the how a supercapacitor can be fabricated. Okay, so we can fabricate a supercapacitor in sandwich type of geometry. So suppose we have our material, any electrode in powder form. I can I can make a gel or slurry out of this powder material by dispersing this carbon powder either in ethanol or dimethyl formula DMF. Okay, so once slurry is formed, I can paste this slurry on my current collectors. Okay, these current collectors can be of aluminum or stainless steel, or you can even use carbon substrate and you can coat your material on carbon substrate. So after coating this slurry of this material on the electrodes, okay, you can prepare your device in sandwich type of geometry. For example, you can see these are current collectors. On the top is carbon paper, and on the carbon paper we can coat some material, and we can do this type of arrangement, and we can lock this close this device. Okay, and this device is this is a two electrode device, so we can perform various electrochemical techniques on this device. For example, in cyclic voltammetry. Okay, so cyclic voltammetry is a potentiodynamic technique. Okay, so we can perform cyclic voltammetry in on two electrode system or in three electrode system. Okay, so what we do in this cyclic voltammetry technique, we know the capacitor. Okay, so capacitor current is given by I C dV upon dt. Okay, so if we scan the voltage. Okay, when we have device, okay, we can connect it this is a working electrode, this is our auxiliary electrode. So we can short auxiliary electrode and reference electrode and a working electrode, and we can apply a ramp of voltage to this device. Okay, so when we apply this scan and ramp of voltage, this is dV by dt, starting from initial voltage to some final voltage. So for example, I'm using water based electrolyte, then I cannot go more than 1 volts. Okay, as I already told, if you go up beyond 1.2 volts, water start decomposing. Okay, so I can go up to 1 volt. If I'm using gel electrolyte or we are using ionic liquid, then I can go up to 3.5 or 4 up to 4 volt. So I can start with some voltage, and I can set my voltage with a fixed scan rate. So when this scan rate is fixed, okay, so this will give me constant current. So if I'm assuming this given potential window, my capacitance is constant. Okay, suppose there is no redox process happening, this is the ideal capacitor. Then if I'm applying a constant scan rate, I get constant current. For example, so suppose this I'm giving this 20 millivolt scan rate. Okay, so I'm getting this curve. This is the rectangular curve. Okay, so CV curve, cyclic voltammetry curve for a capacitors are generally ideally rectangular. Okay, so here you can see this rectangular shape. This is the ideal capacitor behavior. Okay, now if my supercapacitor is not ideal, okay, if it has a high resistance, okay, resistor character, then I won't get this rectangular shape. Okay, instead of rectangular shape, I will get some tilted rectangular or tilted ellipse. Okay, of course no capacitor is ideal. Okay, they have some resistance. So like carbon based material, they generally show this almost rectangular type of behavior. So once you have this rectangular type behavior, you know the current. Okay, you can easily measure the current. So you know the scan rate. Okay, and from the plot you can calculate this current value, and from this you can calculate what is the capacitance of device. Okay, and you can perform this experiment with different scan rates. Okay, you can perform this scan rate with different scan rate, and with each scan rate you can calculate what is your capacitance value. So ideally, if your material is very conducting, okay, you will get always constant capacitance value. But in general, when you increase the scan rate, your capacitance values also decreases because of the kinetics. Okay, so suppose if it is a double layer material, so when you are scanning very fast, your ions cannot move, cannot respond to this scan rate. Okay, because ion has to go through the pores of the material and access the surface area. If this scan rate is very high, very fast, then ion cannot move that much fast. Okay, that will show some resistance. Okay, and because of the resistance, current will decrease, and your capacitance values also will decrease. Okay, similarly, if you are using some pseudo capacitance material like metal oxide, you are using some conducting polymer. In that case also, because the redox reactions, they are not very fast. Okay, they will always they are slow charge transfer reactions. Okay, so when high scan rate, either you are applying high voltage voltage scan rate or high current. Okay, in that condition the material will not able to respond so fast. So your current values will decrease. Your current, so suppose you're making 20 and out of 40, so current will ideally current should become double. Okay, but current will not get double, it will show some 1.5, 1.8. On some material even can show proportional increase in also current if the conductivity is very good. For example, with thin oxide materials. Okay, and quality prepared graphene sheet also can show proportional type of behavior. So once you have this ideal curve, you can easily calculate, you can measure the current, and you can calculate the capacitance value. But what happens when your material is storing charge, then more than one mechanism? Suppose you have a pseudo capacitance material also, and you have double layer capacitance also material, then you will not get this ideal capacitance type of behavior. Your shape will be like this one, wave like. You will get bumps, wave like or bump like character in your CV. In that condition, it is difficult to measure the current. Okay, so what you can do, either you can measure the current and you can make it average. Okay, or positive side, and similarly you can measure the current and negative side and you can take average. And then finally, if these are symmetric, then you can take any average value. If these curves are not symmetric with respect to zero level, then you need to again take average of these two currents, or simply you can use this formula. Okay, you can take a voltage range and you can integrate this thing. So this can be done very easily in any software. So as I told you, see, if I know scan rate, and if I apply a scan rate, if I measure the current, I can calculate the capacitance values, cell capacitance values. So in supercapacitor, generally capacitance values are given in farad per gram. That means specific capacitance. Okay, so you have to do, because your current depends on your mass, how much mass you are loading on your current collector, what is the mass of electrode. More the mass of the electron, more the current, because you get more the current. Okay, more the electrons. Okay, so when you divide this mass by your capacitance, it will give you a specific cell capacitance. Okay, so this is cell capacitance. Now I told you in the beginning that a supercapacitor is basically has two capacitor in series. Okay, so if I want to calculate capacitance value of only one electrode, okay, so that will be twice of the cell capacitance, because these are in series. Okay, and if this is symmetric capacitor, that means this value is C. So this 1 by C, 1 by C, so they become same, and it will be double of your cell capacitance. Okay, and if you want to calculate the specific capacitance of a electrode, okay, then you have to divide by the mass of the one single electrode. S means single electrode. Okay, so we can see the capacitance of one electrode is four times the capacitance of my cell. Okay, because when I am dividing my cell capacitance, I am divided by m. The m is the total mass. Okay, total mass means the mass of both the electrode. Here I am applying single mass, so already 2 is there, 2 will go up, so it will become 4. Okay, so my CSP, specific capacitance of single electrode, is 4 times the electrode of cell. Okay, now I'll show you some how lab and these kind of experiments are performed. Okay, so So these are the softwares which comes with electrochemical analyzer. So I have used this CH instrument. So for you can see here, suppose I'm taking some old data. So this is suppose 10 millivolt scan rate. Okay. It's not coming. Just give me 1 minute. Okay, so you can see in laboratory how can we perform the experiment. So for CB, we need to apply scan rate. Okay, so for example, what is your initial voltage? Okay, so suppose you want to start from 0. Okay, what is the your maximum voltage? That is cell voltage. If it's a water base, you can go up to 1, and depending on your quality of material. Okay, some of your material may become insulated, like polyolefins. They become insulating when you use voltage more than 0.7. They are decaying it very fast. Okay, so that potential window you need to decide. Okay, कि तुम्हारा voltage window कितना तुमको लगाना है. Okay, so suppose I am starting. This is the ruthenium. I think this is a ruthenium oxide graph. So you can see because these materials show ideal capacitor like behavior. I told you in the beginning, if your material capacity is ideal, it will give a rectangular shape. Okay, so I am applying here initial voltage 0 and highest voltage 1, and I'm here giving a scan rate. Okay, ये कितना scan 10 scan rate देना है, 20 देना है, that is your choice. Okay, now suppose I'm giving 10 millivolt scan rate. Okay, so from 0 to 1 it will take 100 seconds, and again it has to come from 1 to 0, it will take 100 seconds more. So in one cycle total it will take 200 seconds. Okay, so if you want to make it 6 cycle, 10 cycles, it depends on you. Okay, according it will take time. So you can scan your voltage for given scan rate. Okay, now also you can change the scan rate. So just now I shown you the graph with 10 scan 10. So you can also show with 20 also. So this is with 20, this is with 20. Okay, so as you increase the scan rate, your area of this curve will also increase, your current will also increase. Now this increase in current should be proportional. Okay, suppose now it is showing around 5. Okay, so earlier it was 3, so ideally it should become 6. Okay, but as I told you, because of charge limitation of charge transfer kinetics. Okay, you will not get the proportional current. Okay, exceptional in some cases you can get almost proportional current also. So this is the one way of characterizing your material. Okay, so characterizing your supercapacitor device means you can calculate capacitance using this cyclic curve. Okay, so you can do it 10, 20, 50, 100 milli scan rate, and for each scan rate you can get the plot, you can get the current values, you can calculate the cap. Hello. So I was showing how to perform these experiment in on a electrochemical analyzer. I am showing the old datas. Okay, so you need to apply this the parameters. So if you want to get the CV, okay, so you need to fix the initial and final values, like it should start from 0, it should go up to 1, and then you can fix your scan rate. Okay, so suppose you want to go from 0 to 1 and scan rate is 10 millivolt, so it will take you around 100 cycles to complete this cycle. Okay, and then again you have to come from 0 to 1. Okay, so 0 to 1, in that case what will happen, it will take almost 200 cycles to complete one cycle. Okay, so this is now on we have done on 10 millivolt per 10 millivolt scan rate. You can also increase the scan rate, you can go up to 50 and 20 millivolt also. So when you go 20, okay, your current will increase, the area of this cycle will increase. That means it's showing that your capacitance also the capacitance will be almost constant, or it will decrease, because you are doubling the scan rate, but current is not getting doubled. Okay, so with the increasing scan rate, your capacitance value will decrease, and this is called the rate capability of your material. Okay, how your material is performing in when high you are applying high scan rate or high discharge rates. Okay, so this is all about cyclic voltammetry. Okay, cyclic, with using the cyclometric voltammetry, you can calculate the capacitance, you can also calculate the active surface area of your material or catalysis. For that I will provide the another link. Okay, so I'm not explaining these things here. And now the second technique is chronopotentiometry. Okay, so chronopotentiometry or charge discharge. Okay, so as I told in the beginning, in cyclic voltammetry, so in cyclic voltammetry you are applying scan rate and you are measuring the current. Okay, so in chronopotentiometry we do different way. Instead of applying scan rate, we provide the constant current to the device. Okay, and we measure the change of voltage of which we'll charge the device, and finally we'll discharge the device, and from these characteristics also we can calculate our capacitance value. So in industries generally this chronopotentiometry or charge discharge technique is used to estimate the specific capacitance value. So I'll show you the one graph. So say this is okay, so this is my charge discharge cycle of a capacitor. Okay, so suppose here the cathodic, the data, you can see the parameters. So there will be cathodic current, anodic current. So I have given this is 0.0025 ampere, that is 2.5 milliampere. Okay, so so when I apply constant current, okay, so you know c is equal to I dv dt. Okay, so what will happen when I'm applying constant current, my scan rate is positive. Okay, that means now my capacitor start charging. So when I apply this anodic current, my potential of this my electrode cell will change. So I can fix here my maximum and minimum voltage. So my highest limit is 1, my lowest limit is 0. Okay, so when I'm applying fixed current, so when I'm applying positive current, my voltage will rise, and when it reaches to 1, okay, the direction of current will change. So once I change the direction of current, my device will get discharged. So these are called charge curve and charge curve and discharge curve. Okay, and you can plot any number of cycles. For example, here I have done this experiment for 10 cycles. Okay, so in order to check the stability of your electrode, you have to run these cycle up to 10,000 5,000 cycle, and then you have to show the stability of your graph. Okay, so for what we can do from this graph, once we have to take this discharge curve. These are the discharge curve. Okay, so for ideal capacitor this should be linear curve. Okay, so from this is almost linear, so you can calculate the discharge time. Okay, so once you know the how much time it takes to discharge for a given current. Okay, for given current value, how much time your device takes to discharge, from there also you can calculate the capacitance values. Okay, and similarly, like we do the charge discharging, the cyclic voltammetry different scan rate. Okay, you can also perform this charge discharge also in different current rates. So you can see there's a sudden drop in the this discharge curve. This is called IR drop. Okay, and this IR drop, okay, this shows the resistance and it increases with the increase in current. Suppose I have shown you 1 ampere per gram. Now I'm showing you this 5 ampere per gram. Okay, so you can see when I increase the current. Okay, so again it will discharge, and you can measure the capacitance or different current rates, but then this voltage drop will also increase. Okay, that means this is not useful voltage. Okay, that means now your cell voltage is not 1. Okay, you have to reduce this much amount from your cell voltage, so the cell voltage become only 0.94. Okay, so when you're calculating energy density values on each current, then you have to calculate this IR drop also in final estimation of your energy density of your material. Okay, and finally, as you increase the scan, as you increase the current loading, okay, your capacitance value will also decrease, because your discharge time will not decrease by proportional in proportion. For example, now I show you some. So this capacitor, suppose I want to check the stability of my electrode. Okay, so this is 1 ampere per gram after 1000 cycles. So in the first cycle, how much was my capacitance? Okay, and when I run 1000 cycles, after 1000 cycles, what is my capacitance? Okay, that means I will measure the discharge time, and I will measure the capacitance retention capability of my material. Okay, so I will also show you how to perform this 1000 cycles. So this is 1000 cycles curve. Okay, so in order to show that my material is stable, okay, so generally we do perform up to 5000 cycles. So here I'm showing this 1000 cycles. So you can see, you can enlarge and you can check. So these are the thousand cycles. Okay, so you can start from the first cycle, and you run this 1000 cycles, and after 1000 cycles you can measure the capacitance values. Okay, if this capacitance retention is very good, okay, generally your supercapacitors gives up to 80 to 90% retention. Okay, that's why I told in the beginning that their cycle life is very high. If you use batteries, okay, they will fade away very easily within a few hundred cycles. Okay, so you can measure this discharge time. From there you can calculate the capacitance values. Okay, so I'm again going back to my slides. So this was the cyclic voltammetry in charge discharge. Okay, you can measure the delta T value, that is the discharge time, okay, for given constant value. Okay, voltage window, you know what that is, a B cell. Okay, so if you know these parameters, you can calculate your cell capacitance value. And if you once you know the cell capacitance value, from there you also can calculate energy density value, power density values. Okay, so these are the two techniques we generally use for estimation of capacitance. Okay, so this chronopotentiometry, this is an industrial technique. In industry also they use this technique to characterize your supercapacitor. Okay, so now last technique which I want to discuss, that is impedance spectroscopy. So in this technique, what we do, we apply a sinusoidal input to our device with various frequency range, and we will measure the response of the material. Okay, we plot a graph between real part and imaginary part of impedance. So for example, for ideal capacitor, if you have a conventional capacitor, ideal capacitor, so ideal capacitor do not have any resistance. Okay, so we know the omega C, we know that omega C cell. Okay, so C is equal to 1 by omega Z, or Z equal to 1 by omega C. Okay, if that is for an ideal capacitor. So if an ideal capacitor, I plot Z dash Okay, Z dash versus this is the real part, this is the imaginary part. So real part is generally resistance. Okay, so if you plot 1 by Z versus 1 by frequency, I'll get a straight line. This is why ideal capacitor. Okay, but our super capacitor is not ideal. It has some internal resistance also. Okay, and this they do also show diffusion resistance also. So electronically, if my super capacitor will start from this line. Okay, this is called a Warburg resistance. Okay, Warburg region. So my super capacitor will start from the 45 angle, and at low frequency this will become again a straight line. It will show like ideal capacitor like behavior in low frequency range. So if we want to measure, we want to fit this data. Okay, so we need some electronic equivalent circuits. Generally people try to use this circuit. Okay, where to fit their device data. So this is the double layer capacitance, this is the RP, is the diffusion resistance. Okay, the RP is this one, charge transfer resistance, and this is the diffusion resistance, and this is the ESR, series resistance. Series resistance means your what is your electrolyte resistance, what is your electrode resistance. So those things you can measure. Generally impedance perform to measure this ESR. That's a very important parameter for supercapacitor device, which limit your power delivering capability. So we can measure ESR values. Okay, and if we take low frequency region. Okay, so in low frequency region we can fit the data with a straight line, and the slope of the graph will give you the capacitance value. So these all three capacitance value you can get from CV and this chronopotentiometry and impedance. Okay, ideally they should match, but they will never match, because there are slight difference in how do you perform the measurement. So generally in literature people show the capacitance value which they achieved by charge cyclings. Okay, and one more thing, and this all the properties or all the behavior of the supercapacitor is not be shown by only one equivalent type of resistance. Okay, so because generally why my experience is for supercapacitor, this fitting is not always perfect. Okay, we can show we can get some insight by fitting these kind of circuits, but generally it is very difficult. If you take battery, it can easily fit in any equivalent circuit. For supercapacitor, generally the fitting is not that much accurate. So now I will show you some my data what we have done, like cyclic volt. This is the magnesium dioxide. So I am performing this of different scan rate. Okay, and I'm measuring the specific capacitance. So this you can see as I'm increasing the scan rate, okay, or current density. Okay, my capacitance values are decreasing, and from this curve I can calculate at what current, what is the IR drop. Okay, and similarly you can see here I have plotted only discharge curve. Okay, so we have charge curve, discharge curve. So capacitance values are generally always calculated using this discharge curve. Okay, similarly I have shown you this is the impedance curve. Okay, so our supercapacitor shows almost ideal capacitor like behavior. They start from the 45 angle, and then it goes vertical. Okay, so and this you can see the ESR value, this is 0.6 ohm. So generally in supercapacitor ESR value is also very small, so that's why they show very high power densities. So we can also calculate the capacitance value with respect to frequencies. So in impedance, so you can each frequency you can calculate what is your capacitance values, and you can plot and you can show variation of capacitance with frequencies. Okay, and then you can calculate and these are CVs. Okay, cyclic voltammetric curves. So as I told you, you conducting polymers, they don't show ideal capacitive like behavior. This is the pure polymers. This is pure polypyrrole. This is the polyparaffin diamine. So these electrodes are not showing, and they are showing pseudocapacitant type of behavior. So and when we carbonize these material, okay, when they become carbon, okay, their characteristics will change. You can see they are showing ideal rectangular behavior at low current, because resistance is low, so they show almost rectangular behavior. As you change the high scan rate, resistance is increasing, and they deviate from their rectangular characteristics. Okay, so you can perform experiment on different charge rates. You can calculate the, you can see the rate capability of your material. You can check the cyclic life. Okay, and also you can plot Ragon plots. So Ragon plots are basically plot between a energy and power density. So when you so in each current, okay, you can calculate what is your energy density, okay, and then you can calculate what is the or fuel cell. Okay, so generally I told you that your capacitor do not show any semicircle. Okay, this is called charge transfer resistance. Okay, so but sometimes what happens when your carbon material has a functional groups, okay, or some defects are there, so then they show very small charge transfer. Okay, you can see this, these are the when I carbonize polymers. Okay, so when you carbonize, they show some increase in the charge transfer resistance because of the defect created by this carbonization and activation process. Okay, so in general they show very small semicircle. This is charge transfer resistance, and low frequency they show ideal capacitive like behavior. So these are the some graph of ruthenium oxide material, okay, which show ideal supercapacitor behaviors. Okay, so I want to stop here. So if you have some question, you can ask.
Hello.
जी मैम.
Any
Hello.
question from the participant side? Hello. If you have any question, you can chat, you can message in chat box. I think no question is from participant side. Thank you so much, Dr. Jaidev, for presenting such a nice tutorial in third GIAN program at Jabalpur Engineering College, Jabalpur. Thank you so much.
Thank you, ma'am. Thank you very much, ma'am.
I think one question. Oh, thank you so much for joining with us. Dear participants, we'll have the last day. Tomorrow we'll have the last day session of third GIAN program. We'll have 2 lectures tomorrow. Then we'll have a small valedictory function in virtual mode. Thank you so much.